Welcome to Sleeping with Science. You have arrived at a quiet place, a place where the rush of the day can soften and the night can stretch without demands. This recording is here for you to rest with. You may drift into sleep quickly, or you may remain awake for a time, letting your mind follow the flow of words. Either way is perfectly fine. Sleep will come when it is ready, and until then, you are simply listening, absorbing, and floating along with thoughts about the universe. Before we begin our journey, I kindly invite you to like this video and subscribe to the channel. By doing so, you help us continue creating more stories of science designed to guide you into calm and peaceful nights. Our theme tonight is infinity, the infinity of space. It is a word that feels vast even before we try to define it. People have whispered about it since the earliest nights, staring upward at skies filled with more stars than they could count. Infinity can mean endlessness, something that stretches without limit, but it can also mean boundlessness, a space with no borders, no edges, no final wall to touch. These two senses of infinity live together in our imagination, and both are useful as we try to understand the universe. When you step outside on a clear night and look upward, you see a dome of stars. For thousands of years, humans wondered if that dome was real, a ceiling enclosing the world. Yet each advance in astronomy peeled back the illusion. Telescopes revealed more stars, more galaxies, more detail, until the dome dissolved into depth. The sky is not a wall but a window, and what it reveals is larger than any mind can easily hold. Infinity is not always about numbers or distances. It is also about the way our understanding stretches. Each question answered creates new questions beyond it. Early stargazers asked how high the heavens were. Today, scientists ask how space itself is shaped, whether it curves, whether it folds, whether it might be finite yet without an edge. The idea that something can be without limits but also without borders is not simple, yet it is part of what makes infinity so compelling. Tonight, as you listen, you are invited to let these thoughts drift like constellations across your mind. There is no need to hold on to every fact or every explanation. Let them wash through gently. Some will stay with you, others will fade into dreams. Infinity is like that, too large to hold all at once, but gentle enough to be touched in fragments. And here, at the beginning of our journey, we are simply opening the door to it. When ancient people looked up at the night sky, they saw not depth but surface. The stars glittered like jewels on a vast, dark canopy, a dome suspended above the earth. To many cultures, it seemed natural to imagine this dome as a roof solid, protective, perhaps even touched by the hands of gods. The horizon formed a neat line where sky and ground met, giving the impression of a closed world, perfectly bounded. For generations, myths and stories explained this ceiling. Some said it was crystal, others that it was woven fabric, or even the shell of a great cosmic egg. But as careful observers began to track the motions of stars and planets, cracks appeared in the idea of a hard dome. Patterns shifted, planets wandered, and eclipses revealed a more intricate dance than a ceiling could explain. With time, the dome gave way to depth. Telescopes, first modest and then mighty, showed stars that were not set into a surface but scattered through space. The heavens transformed from a roof into a landscape, stretching farther and farther the closer we looked. And yet, even with this deeper view, the question of edges remained. If the dome was an illusion, what replaced it? Did the universe itself have an edge? Could you travel to its farthest boundary and touch it like a wall? The question is simple in phrasing, but the answer unsettles the imagination. Today, cosmologists speak carefully about borders. The universe, as we observe it, does not appear to end at an edge. Instead, it extends in all directions, its expansion carrying galaxies further apart. The mind resists this idea because we are accustomed to boundaries. We live in rooms with walls, on lands with shorelines, on a planet with curvature we can walk around. Infinity is difficult precisely because our everyday lives are finite. One way to sense this paradox is to think of Earth itself. If you set out walking in a straight line, you never fall off the edge. You may walk endlessly, circling the globe, yet the surface is finite. The Earth is bound, but unbounded. Cosmologists suggest that space may behave in a similar way, though on scales beyond our reach. It could be finite in volume, yet without an edge to encounter. The celestial dome, then, was not entirely wrong. It was simply a first attempt to describe an experience too immense for simple eyes. In a way, it was an expression of humility. Humans sensed the vastness and drew a shape to hold it. Today, our shapes are mathematical, involving curvature and geometry, but the intent is the same. We are trying to describe a reality that is boundless to us and perhaps infinite in itself. As you let these thoughts settle, imagine the sky not as a roof but as a gateway, open in all directions. You do not need to grasp its full extent. It is enough to know that the dome has lifted, that beyond it lies not a wall but a mystery, unfolding endlessly. Every glimmer in the night sky is more than brightness. It is a message. A photon, the smallest particle of light, was released long ago and has journeyed across the vastness of space to touch your eyes. In that instant of contact, you are linked not only to a distant star but also to a distant moment in time. Light does not arrive instantly. It travels at a finite speed, the fastest speed the universe allows. Because of that limit, when you look upward, you are never seeing the present. You are always gazing into the past. Take the moon as an example. It feels close, yet the light reflecting from its surface takes just over 1 second to reach Earth. When you see its glow, you are seeing it as it was a moment ago. The sun sits farther away, and its light needs 8 minutes to bridge the distance. Every sunrise is already history when it reaches your eyes. Stretch that scale farther, and the lessons of time become profound. The nearest stars reveal themselves as they were years ago. The nearest galaxy, Andromeda, shines with light that set out more than 2 million years in the past. By the time that glow reaches us, entire ages have shifted on Earth. This time-traveling quality of light means that telescopes are not simply tools for magnification. They are time machines. Each additional meter of glass, each improved sensor, allows us to look deeper into history. When astronomers build great observatories, they are not only seeking more distant galaxies, they are reaching for younger versions of the universe itself. The light from galaxies billions of light years away shows us the cosmos in its infancy, filled with stars just beginning to burn. Infinity makes itself known here in 2 directions at once. Distance stretches outward without end, but time stretches backward as well. To follow the path of light is to follow history written into the fabric of space. Each photon carries with it the memory of its birth, the collapse of a star, the glow of a nebula, the collision of galaxies. Space becomes a library where beams of light are books, each one traveling patiently, unhurried, until they meet a reader. For the listener, it is enough to rest in this thought. When you see starlight, you are touching the past. The sky is not a fixed pattern of present-day points. It is an archive, a flowing record, and you are one of its observers. Some stars you see have already died, their light still on the road, their final words still crossing space. Others will shine for millions of years, their messages ongoing, waiting for future eyes to catch them. So, as you close your eyes or let them rest softly on the darkness of the room, remember that light is still traveling above you. It has been traveling since before there were humans, since before there was Earth itself. The infinity of space is not silent. It is speaking always, in beams of light that stitch time and distance into one continuous journey. The mind was built for small things. We are comfortable with meters, minutes, and meals. We can picture the span of a room, the time it takes to walk a street, the weight of a loaf of bread. But beyond that, our imagination begins to tremble. The universe, however, lives on scales that laugh gently at our human instincts. To travel from the small to the vast, we need a different kind of ladder, one made of powers of 10. Begin with a single grain of sand, tiny, barely visible in detail. Place 10 of them together, then 100, then 1,000,000, and suddenly you hold a beach. Expand again, and you have dunes that stretch for kilometers. Our minds can manage this for a while, but when the scale leaps from human to planetary, something shifts. The Earth itself, though massive, becomes a dot compared to the Sunday. The sun, in turn, is a spark compared to the great stars, and those stars are only specks when gathered into galaxies. Astronomers often use what is called a logarithmic scale to cope with this runaway growth. Instead of counting by ones, we count by tens, then by hundreds, thousands, millions, and billions. Each step is not equal in size, but equal in ratio. This is the only way to hold the immensity in thought. One unit up the ladder may be 10 times larger, or 100 times, depending on the rung. And so we climb, from meters to kilometers, from planetary orbits to light years, from galactic spans to superclusters stretching hundreds of millions of light years across. At first, infinity here feels intimidating. The steps grow so fast that you may wonder how far the ladder can go before breaking. But what is striking is not only the distance, it is the repetition of pattern. Stars gather into galaxies, much as people gather into cities. Galaxies link into filaments that resemble threads in a web. The infinite is not chaos but structure, repeating motifs visible at every level, scaled up like music played in higher keys. There is comfort in this symmetry. The same physics that keeps an apple bound to Earth keeps planets bound to stars, stars bound to galaxies, and galaxies bound in their silent dances across superclusters. Infinity is not beyond our reach entirely. Its rules echo in the small, allowing us to sense the large. If you find your mind tiring, allow it to rest. You do not need to climb every rung tonight. It is enough to know that such a ladder exists, and that humans, fragile and brief, have begun to chart it. The infinite can be overwhelming if approached all at once, but when seen as a sequence of steps, it becomes a rhythm like breathing in and out, like drifting into sleep one slow breath at a time. And so we scale the universe, not to conquer it, but to touch its shape in passing. Each rung is a reminder. Infinity is not a single leap, but a gentle progression, one power of 10 after another, without end. Across the entire sky, faint and invisible to your eyes, there is a glow that never goes out. It is not the light of stars, nor the scattered shine of galaxies. It is older than both. It is the cosmic microwave background, a whisper from the first few 100,000 years of the universe, stretched and softened by nearly 14 billion years of expansion. Scientists describe it as the afterglow of creation, the residue of a time when the cosmos was still glowing hot, filled with a sea of light. In the earliest moments, the universe was so dense and energetic that matter and light could not separate. Photons bounced endlessly from particle to particle, unable to travel freely. Space was an opaque fog, but as the universe expanded, it cooled, and atoms formed. Suddenly, light could break away and move unhindered, filling all of space with its quiet radiance. That light has never stopped traveling. It has stretched with space itself, growing weaker and softer, until it now hums gently in the microwave spectrum far below what the human eye can detect. Astronomers first discovered this background accidentally in the 1960 seconds, when two researchers noticed a persistent noise in their radio antenna. It came from no star, no galaxy, no earthly interference. Instead, it came from every direction, equally present wherever they pointed. They had stumbled onto the faint memory of the beginning. What once was searing brightness is now a nearly uniform bath of radiation, only 3 degrees above absolute zero. Yet within that uniformity are patterns. Tiny fluctuations, only fractions of a degree, hold the seeds of everything we see today. Those slight variations in temperature reflect tiny differences in density in the early universe. Over billions of years, gravity amplified those differences, pulling matter into clusters, galaxies, and stars. The grand structures of the cosmos, the web of galaxies, the filaments of clusters were all sketched first in those delicate ripples. Infinity shows itself here not as vast distance but as depth of memory. The universe carries within it a record of its own earliest moments, encoded in radiation that still surrounds us. To study it is to listen to an echo so faint and so old that it defies our usual sense of time. Every measurement of that background is a reminder that nothing is entirely lost. Even the first light still lingers, softened but enduring. You do not need to hold on to the details. It is enough to know that the cosmos has a memory, and that it has carried that memory across billions of years to the present moment. The stars above may rise and fall, galaxies may collide, but beneath it all, this quiet glow remains. The silent echo of the beginning is not gone. It is with us still, wrapped around the earth, filling the infinite with its hushed reminder that every moment leaves a trace. Before we continue, let us pause for a moment. Take a slow breath in and let it out at an easy pace. If sleep has already begun to touch you, allow it to arrive. If not, there is no need to chase it. The words will continue like a calm river, and you may drift along with them until rest comes naturally. Now, let us think about horizons. On Earth, the horizon is where your sight meets its limit. It is not a wall, only a boundary of perspective. If you climb a hill, the horizon moves farther away. If you take to the sea, the horizon bends around you, always shifting yet never vanishing. Horizons are not endings, they are reminders that vision has a reach. In the cosmos, horizons take on a deeper meaning. The most profound of them is the cosmic horizon, the ultimate distance from which light has had time to reach us since the beginning. Beyond that limit, galaxies and stars may exist, but their light has not yet crossed the immensity to arrive here. No telescope, no detector can reveal them. They remain hidden, not because they are absent, but because time itself has not been long enough for their messages to arrive. This is one of the quiet lessons of infinity. Boundlessness does not mean accessibility. The universe may extend without end, yet we can only see as far as light has traveled since the dawn. That distance, though unimaginably vast, is still finite. It forms a sphere around us, an invisible shell marking what is observable. Scientists call it the observable universe. Though the phrasing hides a truth, it is not a universe at all, but a horizon drawn by time and light. Imagine it as a shoreline. You stand on the edge of a great ocean. The waves stretch to the distance, and you know the water continues far beyond what you can see. Yet the line where sea meets sky marks your present limit. You may sail outward, and the line will recede, but there will always be a place you cannot reach with your eyes. The cosmic horizon is such a shoreline, but one we cannot cross, no matter how far or fast we try to travel. There is a gentle comfort in this boundary. It means that what we know is framed, that our vision has an edge. Infinity is not always overwhelming. Sometimes it is softened by limits, by contours that help us take in what otherwise would be too vast. When astronomers map the universe, they do not attempt to capture the endless. They chart the observable, the portion given to us by the speed of light and the age of time. As you let this thought rest with you, notice how horizons guide rather than constrain. They invite us to look as far as we can, to wonder about what lies beyond, and to accept that some mysteries remain outside our reach. The cosmic horizon is not an obstacle. It is a gentle threshold, reminding us that infinity is both near and far, both revealed and hidden. When people hear the phrase Big Bang, they often imagine an explosion, fire, sparks, and fragments hurled into empty space. Yet the reality is more subtle and perhaps more astonishing. The universe did not burst into an already existing void. Instead, space itself expanded. There was no outside into which matter rushed, no central point from which everything flew outward. Every place, every direction, every corner of the cosmos was part of the unfolding. In its earliest fraction of a second, the universe was unimaginably dense and hot. Temperatures soared far above what even the cores of stars reach today. In that state, matter and energy were not yet distinct. Fundamental forces were tangled together in ways that remain mysterious. Then expansion began, and with it, cooling. As the cosmos stretched, particles formed, forces separated, and structure began to take shape. The growth was not into something, but of something the very fabric of space, stretching like a surface pulled taut. A useful image is a rising loaf of bread. As the dough swells, raisins embedded within it move apart. None of the raisins are at the center of the expansion. Each one simply finds its neighbors drifting farther away. Galaxies in the universe behave in a similar fashion. From any vantage point, all other galaxies appear to recede. There is no privileged center, only a universal expansion that touches everything. This expansion continues today, Distant galaxies slide away from us, their light stretched into longer, redder wavelengths. The farther they are, the faster they recede. This is not because they are traveling through space at great speed, but because the space between us and them is increasing. Expansion itself is the motion. Infinity enters here in a quiet paradox. The universe may be finite in age, about 13.8 billion years old, but its extent could still be endless, a young cosmos, already unbounded. This is the subtlety the phrase Big Bang hides. It was not a bang into emptiness, but a steady, everywhere at once unfolding of distances. For scientists, understanding this required a shift in language. Words like explosion mislead because they imply a center, a before, an outside. The expansion has no outside. Asking what lies beyond the universe is like asking what lies north of the North Pole. The question seems natural, but it presumes a direction that does not exist. To sit with this thought is to accept both clarity and mystery. The expansion of space is measurable, charted with precision by astronomers. Yet the reason why the universe expanded, why it has the properties it does, remains beyond full explanation. The Big Bang is both knowledge and invitation, a story we understand in part, and a frontier that continues to beckon. So when you hear the phrase, "Let go of the image of fireworks against a dark sky," think instead of unfolding, of stretching, of a fabric becoming more spacious with every moment. The beginning was not a violent burst, but the quietest of miracles, space making room for itself, and with it, for everything to come. When we wish to know how far away something is, we often reach for a ruler or a tape measure. In everyday life, this is simple. The desk is 1 meter long. The room is 4 meters wide. But in the cosmos, distance cannot be measured by stretching a line from here to there. Space itself is shifting, and the objects we wish to measure are often unimaginably far away. Astronomers needed a new kind of ruler, one written into the light itself. That ruler is called redshift. Light, though it seems steady, carries within it a wavelength the length of its waves. Blue light has short waves, red light longer ones. When a source of light moves away from us, those waves are stretched, sliding toward the red. It is similar to how the sound of a siren drops in pitch as an ambulance passes by. With light, the effect is cosmic. Galaxies racing away under the expansion of space leave their fingerprints in shifted colors, their spectra tilted toward the red end. By measuring this shift, astronomers can calculate not only speed but distance. The greater the redshift, the farther the galaxy, and the longer its light has traveled. Each tiny tilt in color becomes a marker on the scale of the universe. In this way, the cosmos offers its own built-in ruler, written in the glow of stars and galaxies. To refine this ruler, scientists also rely on what they call standard candles, objects of known brightness, such as particular kinds of exploding stars. If you know how bright something truly is, and you measure how dim it appears, you can work out its distance. Combined with redshift, these methods allow astronomers to chart space like navigators on an infinite sea, plotting positions across unfathomable distances. Infinity appears here not as chaos, but as order revealed through subtle signs. A galaxy may be billions of light years away, yet a faint reddening of its light can bring it within the grasp of calculation. The most delicate shift becomes a map of the largest scales. The cosmos whispers its structure not through walls or edges, but through wavelengths, stretched by the expansion of time and space itself. For the listener, the important thought is not the mathematics, but the poetry. Every glimmer in the sky carries with it a code, a quiet signal of how far it has traveled and how the universe has shaped its journey. The night is not random sparkle. It is a chart, waiting to be read. And so, with redshift as a ruler, astronomers extend their vision across billions of light years, tracing the spread of galaxies and the expansion of the universe. Each observation adds another notch on the cosmic scale, lengthening our reach into infinity. No telescope touches the edge, but with light itself as guide, we measure what otherwise would seem immeasurable. When astronomers studied the spinning of galaxies, they noticed something peculiar. The stars at the edges moved far too quickly. By the laws of gravity, the outer stars should have drifted away long ago, flung outward into space. Yet they remained, circling steadily, as though held in place by a hidden hand. That hand is what we call dark matter, not because it is shadowy or sinister, but because it does not shine. It gives off no light, no heat, no radiation we can detect directly. And yet, its presence is undeniable. Galaxies, it seems, are only partly made of the stars, gas and dust we can see. Surrounding and permeating them is a halo of invisible matter, outweighing the visible by a factor of 5. Without it, galaxies would unravel. With it, they hold together in their elegant spirals and glowing clusters. Evidence comes not only from rotation but also from light itself. When light from distant galaxies passes near a massive object, it bends, just as light bends through a glass lens. Astronomers call this gravitational lensing. By studying the arcs and distortions in such light, they can map the presence of dark matter, even when no visible substance is there. The invisible becomes visible through its effect on the visible. Infinity enters here in the form of hidden structure. The stars you see are only the surface decoration of a far larger design. Like the bones beneath a living body, dark matter provides the framework on which galaxies take shape. Vast filaments of it stretch across the universe, binding clusters together into webs hundreds of millions of light-years across. What we observe as luminous is only a trace on the skeleton of the unseen. For scientists, this raises profound questions. What is dark matter made of? Particles unlike those in our ordinary atoms are suspected, but none have yet been captured. It may be that whole families of particles await discovery, particles that scarcely interact with light yet dominate the mass of the universe. Our instruments strain to detect them, but so far the mystery remains intact. For the listener, the lesson is gentler. Not everything real can be seen. Much of what holds the cosmos together is invisible to our eyes, yet its influence is everywhere. Just as trust, love, or memory shape a human life without being tangible, so dark matter shapes the universe silently, invisibly, but with immense power. When you look up at the stars, you are seeing only the lacework of light woven onto a darker fabric. The infinity of space is not just what glows, but also what hides, the unseen bonds that cradle galaxies and give them form. In every spiral, every cluster, and every filament, dark matter whispers its presence, not in photons, but in the harmony it sustains. In the late 20th century, astronomers set out to measure the slowing of the universe. Gravity, after all, pulls everything together. If galaxies have been flying apart since the Big Bang, it seemed natural that their pace would gradually ease, like embers drifting upward and then falling back. Teams of researchers studied distant exploding stars, expecting to find evidence of this slowing. What they discovered instead was the opposite. The universe was not decelerating. It was speeding up. This revelation was as startling as it was unavoidable. The light from distant supernovae carried a message. Galaxies were receding faster than models predicted. Something unseen was pushing outward, countering gravity's pull and accelerating the expansion of space. That mysterious force has come to be called dark energy. Unlike dark matter, which clings to galaxies and holds them together, dark energy seems to belong to space itself. It is not concentrated in halos or filaments, but is woven everywhere, filling the void uniformly. As space expands, more of it appears, sustaining the acceleration. Galaxies drift farther and farther apart, and the more they separate, the faster the separation grows. Infinity here reveals itself as momentum without end. The universe is not only vast, it is restless. Each passing billion years adds more distance between galaxies, more emptiness between clusters, more acceleration that will not relent. If the trend continues, the night sky of the far future may look very different, its galaxies fading one by one beyond the reach of light. The exact nature of dark energy remains elusive. Some describe it as a cosmological constant, a simple property of space. Others propose fields or forces that shift over time. Observations refine the possibilities, but none yet provide a definitive answer. What is clear is that dark energy dominates the cosmos today, shaping its fate more strongly than all the stars and galaxies combined. To dwell on this is to confront both mystery and humility. We live in a universe where what is most influential is what we understand least. Our ordinary matter, the elements of planets, people, and stars, forms only a small fraction of the total. The rest lies in the unseen. Dark matter binding, dark energy accelerating. There is no need to grasp the equations behind this discovery. It is enough to sense its wonder, that the void is not empty, that silence itself carries a force, that the infinite is not still but in motion. The galaxies are not just drifting away, they are swept by a tide of expansion that flows through the very fabric of space. When you look up and see the stars, you are not only seeing what is, you are also glimpsing what will become. Dark energy ensures that the future is not static but dynamic, that infinity will not settle into quiet but will continue to open wider and wider with every passing moment. If we could rise high above the universe and watch it unfold in full scale, the sight would not be a smooth scatter of galaxies. Instead, it would appear as a grand tapestry, galaxies clustered together in long strands, stretching across space like threads of glowing silk. These filaments intersect at dense knots, while between them lie immense voids, regions almost empty, spanning hundreds of millions of light years. Together, these strands and gaps form what astronomers call the cosmic web. This structure did not appear overnight. In the early universe, matter was nearly uniform, sprinkled evenly with only the tiniest variations. But gravity is patient. Over billions of years, it gathered matter along invisible scaffolds of dark matter, amplifying the faint differences until filaments and clusters emerged. Like rain sliding into valleys, gas and galaxies flowed toward the densest regions, leaving voids behind. The result is a universe that is not random at all, but patterned on scales so vast they defy ordinary comparison. To picture this, imagine the foam on a wave. Bubbles rise, burst, and leave behind delicate films that trace a network of cells. The cosmic web is similar, though its filaments are billions of light years long, and its voids could swallow entire clusters of galaxies without a trace. What looks from Earth like a scatter of stars is in truth part of a grand geometry, where every galaxy belongs to a larger design. Infinity, here, takes the form of connection. Each filament links galaxies across unimaginable spans, tying them together in a network that stretches beyond sight. No single galaxy floats alone. Each one is anchored in the web, a node on strands of invisible matter that weave the universe into coherence. The pattern is so large that our entire Milky Way is just a thread within a much greater fabric. Astronomers map this web by tracing the faint glow of galaxies and the subtle distortions of light caused by gravity. Computer simulations confirm the pattern. Start with the laws of physics, add the ingredients of dark matter and expansion, and the web emerges naturally. The universe, left to its own devices, builds beauty from simplicity. For us, there is a quiet reassurance in this design. In the seeming chaos of night, where stars scatter at random, lies an underlying order. Infinity is not emptiness, but harmony at scales beyond our reach. Just as rivers carve valleys on Earth, gravity has carved pathways across the cosmos, leaving a network that holds galaxies as gently as a spider's web holds dew. When you next think of the universe, try to imagine not scattered lights but strands stretching endlessly, crossing, joining, surrounding vast spaces of silence. The cosmic web is the universe's architecture, a design both delicate and immense, reminding us that infinity can be both vast and beautifully structured. Take a slow breath. Let it ease out. If your eyes are heavy, you can allow them to close. If your mind is still alert, that is welcome too. This is a resting place, not a race, and the story will continue at its own gentle pace. Whether you drift off now or later, the universe will still be here, waiting. When people think of the universe as endless, they often imagine it without limits. Yet physicists speak often of boundaries, horizons, defined not by walls but by conditions. These limits are not fences you can touch, but thresholds written into the laws of space and time. They tell us where we can look, how far we can see, and which events will forever remain beyond our reach. One such threshold is the particle horizon. It marks the greatest distance from which light has had time to reach us since the beginning. Anything farther is not yet visible, because its messages are still traveling. The particle horizon is not fixed. It grows with time as more light completes its journey. Every moment, the observable universe expands, like a lantern gradually illuminating more of a darkened landscape. Another limit is the event horizon, best known around black holes but present on cosmic scales as well. Because the expansion of the universe is accelerating, there are galaxies whose light will never reach us, no matter how long we wait. They are not too far in space, they are too far in time. Their distance increases faster than light can bridge. Beyond that horizon, events unfold, but they are sealed off from us forever. These boundaries are humbling. They remind us that knowledge itself has a scope. We can observe, infer, and model, but there are regions of reality we can never touch, no matter how advanced our instruments become. The word infinite is not always about boundless access. Sometimes it means encountering limits that cannot be crossed. Yet there is comfort in this as well. Just as a shoreline frames the sea, these horizons give shape to our view of the cosmos. Without them, the universe might feel overwhelming. With them, we are given a portion we can hold in thought, a sphere of observation, a window of events, a landscape defined by the paths of light and the flow of time. It is natural to wonder what lies beyond these horizons. The honest answer is that we do not know, but that not knowing is part of the beauty. The universe is not only what is revealed, but also what remains hidden, drawing us onward in imagination. Boundaries do not end curiosity, they nurture it, pointing always to a beyond that stretches farther than we can see. As you let these ideas rest with you, remember, the cosmos is not a closed room, but a space with contours. The edges we encounter are not walls, but thresholds. Gentle reminders that vastness is measured not just by distance, but by the very limits of what can be known. Scattered across the galaxy are vast nurseries where stars are born. These stellar cradles are not neat or quiet places, but enormous clouds of gas and dust, stretching for dozens or even hundreds of light years. Within them, gravity slowly gathers material, compressing it until regions grow dense and hot enough for nuclear fusion to ignite. What begins as a cold, dark cloud transforms into blazing points of light. These places are often called star factories because they produce the engines that power galaxies. The process begins with hydrogen, the simplest and most abundant element in the universe. As atoms are pressed together under gravity's insistence, they fuse into helium, releasing energy in the form of light and heat. This is the core activity of stars, the steady merging of small nuclei into larger ones. Over time, in the hearts of massive stars, the cycle continues beyond helium, building carbon, oxygen, and even heavier elements. The life of a star is a balance between two forces, the outward push of radiation from fusion and the inward pull of gravity. For billions of years, this balance holds steady, but when the fuel begins to run out, the harmony breaks. Small stars fade quietly into white dwarfs, dense remnants that cool slowly. Larger stars end more dramatically, exploding as supernovae, scattering their enriched contents back into space. These explosions are both violent and creative. They spread the heavy elements forged in stellar cores across the galaxy, seeding future generations of stars, planets, and eventually life. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were shaped in ancient stars that lived and died long before Earth existed. To reflect on this is to see life itself as part of a cycle larger than any single world. Galaxies, then, are not static collections of stars. They are ecosystems, with clouds collapsing, stars igniting, and remnants enriching their surroundings. Over billions of years, this cycle repeats, turning hydrogen and helium into the rich variety of elements that compose the periodic table. Every bright star is a link in that chain, every supernova a scattering of possibilities. The scale of this process is immense, yet the principle is simple. Matter transforms, and in its transformation, it creates the conditions for complexity. The infinity of space is filled with these factories, operating ceaselessly, building the ingredients of planets, oceans, and living beings. It is easy to look up at the stars and see only points of light, silent and distant. But in truth, each one is part of a great workshop, a furnace where atoms are joined, energy released, and matter reshaped. When you look at the night sky, you are looking at creation in progress. Not in myth, not in metaphor, but in the quiet, ongoing labor of physics, repeating endlessly across the galaxy. Among all the strange objects in the universe, few capture imagination as powerfully as black holes. They are not holes in the usual sense, nor do they behave like ordinary objects. Instead, they are regions where gravity is so intense that nothing, not even light, can escape. Matter collapses inward, compressed beyond recognition, until it passes a threshold called the event horizon. Beyond that horizon, no information returns. It is the ultimate boundary, a place where knowledge itself seems to stop. Black holes form when massive stars reach the end of their lives. After burning through their fuel, gravity overwhelms their cores, pulling everything inward with irresistible strength. The collapse is complete, and the star's mass is compacted into an unimaginably small volume. From the outside, what remains is not a visible surface but a horizon, a one-way border. Anything crossing it vanishes from the view of the universe, leaving only silence. Although invisible, black holes reveal themselves through their influence. Gas spiraling toward one forms an accretion disk, heating to extreme temperatures and shining brilliantly in X-rays. Sometimes, jets of material shoot outward from the region around the horizon, stretching across light years. Ironically, what marks the presence of a black hole is not darkness, but the blazing processes at its edge. Scientists describe black holes with elegance and caution. Their properties are summarized by just a few numbers: mass, spin, and charge. Yet around them swirl mysteries that challenge our understanding. What happens to information that crosses the horizon? Does it vanish? Or is it preserved in ways we cannot yet grasp? The so-called information paradox has driven decades of debate, linking gravity, quantum mechanics, and thermodynamics in a puzzle not yet solved. For our view of infinity, black holes serve as reminders of limits. They show us that space is not always open, that boundaries exist where physics itself bends toward the unknown. At the same time, they illustrate the universe's creativity. From stellar deaths come new entities compact, extreme, and essential for shaping galaxies. In fact, at the centers of most large galaxies, including our own, lurk supermassive black holes, millions or billions of times the sun's mass. Their gravity anchors the dance of stars, binding the galactic core. It may sound strange to speak of comfort in such extreme objects, yet there is a kind of reassurance here. Even at the edges of knowability, patterns remain. Horizons are not chaos, they are structure. The cosmos does not abandon order, it simply hides some of its workings from view. When you look up at the night sky, you will not see a black hole with your eyes. But somewhere in that darkness, they exist. Silent guardians of boundaries, sculptors of galaxies, keepers of mysteries. They remind us that infinity is not only about distance without end, but also about depth, places where knowledge itself seems to fold inward, waiting for future discovery. We move through time as naturally as we move through space, yet the two feel different. You can walk forward, backward, or sideways in a room, but you cannot reverse your steps in time. The past is fixed, the future still unfolding, and the present is the only place you can stand. This one-way flow is often called the arrow of time, and it is one of the most profound features of the universe. Physics explains part of this arrow through the concept of entropy. In simple terms, entropy measures disorder, and in every natural process, disorder tends to increase. A glass may shatter on the floor, but the pieces do not leap back together. Smoke disperses into the air, but it never gathers itself neatly again. This steady drift toward higher entropy gives time its direction. It is why we remember yesterday but not tomorrow, why eggs break but do not unbreak, why aging moves one way. Yet time is more than entropy alone. On cosmic scales, Time is shaped by expansion. The universe began in a state of low entropy, hot, dense, uniform. As it stretched, it grew more complex, creating structures and possibilities. Stars, galaxies, planets, and life all arose as byproducts of this unfolding. The arrow of time is thus linked both to the laws of physics and to the history of the cosmos itself. Infinity touches time in subtle ways. While space extends in all directions, time appears to extend in only one. We can imagine infinite space, but can we imagine infinite future? Some models of the universe suggest that time will continue forever, carrying the cosmos toward colder, emptier states. Others propose cycles, expansions and contractions, beginnings and endings repeating without end. In each case, time serves not just as a backdrop but as an active player, guiding the evolution of everything. Our human sense of time is limited, measured in minutes and years, yet the universe measures it in billions. To think in such scales is to step outside ordinary perception. A single second on a cosmic clock might hold the rise and fall of entire civilizations. Against such immensity, our daily concerns shrink, but not in a way that diminishes them. Instead, it can be calming to realize that we are part of a vast current, carried gently along with galaxies and stars, all flowing in the same direction. You cannot stop that flow, nor should you. The arrow of time is the reason stories exist, why music has rhythm, why lives have beginnings and endings. It is the quiet structure that gives meaning to experience. To sit with this thought is not to resist time but to accept it, to let it move as it always has, carrying the universe forward. So as you rest here, think of time not as a cage, but as a current. It moves in one direction, steady and sure, and in that movement, it shapes both stars and moments, galaxies and memories, weaving them all into the same unbroken flow. Take a slow breath. If drowsiness has begun to settle over you, allow it to deepen. If your thoughts remain clear, that too is fine. This is a moment without pressure, a quiet space where wonder can accompany you toward rest. Among the ideas that science entertains, few are as wide in scope as the possibility of multiple universes. Our cosmos, vast as it seems, may not be alone. It may be one region within a greater collection, sometimes called the multiverse. The thought is staggering, yet scientists approach it with caution. Unlike galaxies and stars, other universes cannot be observed directly. Instead, they appear as suggestions from mathematics, byproducts of theories seeking to explain the earliest moments of our own. One line of reasoning comes from cosmic inflation, the rapid expansion thought to have occurred fractions of a second after the Big Bang. Some versions of inflation suggest that while our patch of space stabilized into a universe, other regions may have inflated differently, creating their own bubbles of reality. Each bubble could carry its own laws of physics, its own constants, even its own versions of matter. Our universe, in this picture, is one bubble among many, floating in an infinite sea. Another perspective arises from quantum theory. At the smallest scales, particles behave in uncertain ways, taking on multiple possibilities until measured. Some interpretations extend this uncertainty outward, proposing that every possible outcome exists somewhere, each forming a branching universe. In such a model, there could be countless variations of reality, endlessly multiplying with each quantum choice. These ideas stretch imagination to its limits. It is difficult enough to comprehend one universe with its billions of galaxies. To add the possibility of many universes, each potentially infinite in size, can feel overwhelming. Yet the multiverse is not offered as fantasy, but as a modest proposal to explain certain puzzles: why our universe has the properties it does, why its constants allow for stars, planets, and life. It is important to note, however, that these concepts remain speculative. Evidence for other universes may never be accessible. Our horizons, shaped by light and time, may forever block us from seeing beyond. Still, even as hypotheses, these ideas serve a purpose. They remind us that reality may be larger than we assume, that what we call everything might itself be part of something greater. Whether or not multiple universes exist, the thought is quietly humbling. It shows that even with our best theories, we stand at the edge of knowledge, gazing out toward possibilities we cannot confirm. To sit with this awareness is not to feel small, but to feel part of a continuing inquiry. Science moves forward not only by what it proves, but also by the questions it dares to ask. As you let your thoughts drift, you do not need to decide whether the multiverse is real. It is enough to let the idea float past, like a bubble on a stream, shimmering briefly before moving on. The universe you inhabit is already rich beyond measure. Anything beyond it is an added mystery, gentle and vast, waiting quietly at the edge of thought. When we imagine the universe, we often picture it as an open expanse, stretching outward without form. But physicists ask a subtler question: what is the shape of space itself? This is the field of topology, the study of how a surface can be curved, connected, or wrapped. The cosmos is not only vast, it may also be shaped in ways that defy ordinary intuition. One possibility is that the universe is flat, extending in every direction without curve, like an infinite sheet. In such a geometry, parallel lines never meet, and the rules of Euclidean geometry hold across cosmic scales. Measurements of the cosmic microwave background suggest that our universe is very close to flat, at least within the region we can see. Another possibility is that space is closed, curving back on itself like the surface of a sphere. In that case, if you could travel far enough in a straight line, you might eventually return to your starting point, much as a traveler circling Earth comes home without ever finding an edge. Such a universe would be finite in volume, yet without borders. There would be no wall to reach, no outside to step into, only endless looping paths. Still another model suggests an open universe, shaped more like a saddle, curving outward without limit. Here, parallel lines would eventually diverge, and the cosmos would expand forever, with no possibility of returning to the same point. Beyond these broad categories lie even stranger topologies. Mathematicians imagine universes shaped like donuts, or with complex twists where space folds into itself. In these models, light could circle around, and distant galaxies might appear as multiple images of the same object, seen from different directions. The geometry of space could create illusions, disguising the true structure with repeating patterns. What makes this more than speculation are the tools of observation. By studying the distribution of galaxies and the fine ripples in the cosmic background, scientists search for clues about curvature and connection. So far, the evidence points to near flatness, but with uncertainties that leave room for other possibilities. The cosmos may be simple, or it may be subtle beyond our current reach. Topology matters because it touches the deepest question. Is the universe infinite or finite? If it is flat and unbounded, it may extend endlessly. If it is closed, it may be finite, yet without edges. If it is open, it expands forever in all directions. Each possibility reshapes how we think about space, time, and the ultimate reach of reality. For us, the lesson is not to settle on one vision, but to appreciate the richness of possibility. The shape of the cosmos is not obvious, and it may never be fully known. Yet even asking the question changes how we see the sky. Instead of thinking of space as emptiness, we begin to see it as structure, as something that can bend, loop, and weave into forms as elegant as any geometry drawn on a page. Before we begin, allow your attention to soften. You do not need to hold tightly to every word. Think of this as setting down a weight at the end of a long day. The ideas will flow past like passing clouds, and you may follow them lightly, or let them drift away if rest begins to take over. Infinity is not only a feature of space, it is also a feature of mathematics. Numbers themselves carry infinities, and they come in different kinds. The simplest is the infinity of counting. Add 1 to any number, no matter how large, and there is always another waiting beyond it. This is a countable infinity, a ladder that extends forever, rung after rung, each distinct and ordered. But there are also infinities that defy counting. Consider the numbers between 0 and 1. They are unending too, yet they are not arranged in a neat sequence. Between any two lies another, and between those, more still, without limit. Mathematicians call this an uncountable infinity, and it is larger than the infinity of counting. It is not a ladder, but an ocean, continuous and dense, with no gaps to step upon. The cosmos invites both kinds of infinity into its structure. Stars and galaxies may seem like countable objects, but the space that stretches between them is more like the uncountable continuum. Distances can be divided endlessly. Coordinates have no smallest unit. The fabric of the universe mirrors mathematics, carrying both discrete and continuous infinities within its reach. Some theories even suggest that reality itself branches infinitely, with parallel possibilities spinning outward at every quantum choice. Each decision, each interaction, may cast countless versions of the universe into being. Whether these realms truly exist is uncertain, but the mathematics that describes them is consistent, whispering of realities far beyond our grasp. These reflections do not demand proof tonight. They are offered instead as gentle reminders that infinity is not one thing, but many. It has textures and flavors, ladders that never end, oceans with no shore, branches that multiply without stopping. Each reveals something about how we think, and perhaps how the cosmos itself is built. It is easy to feel lost in these vast abstractions, yet there is a calmness in knowing that infinity surrounds us in familiar ways. A spiral of galaxies repeating across the sky, the unbroken line of time stretching forward, the endless decimals of a number all echo the same theme. Infinity does not have to be overwhelming. It can also be steady, patient, and quietly present. So, as you let your thoughts ease, imagine these infinities not as walls closing in, but as gentle landscapes stretching outward, fields without fences, seas without shores, branches without ends. You may follow them as far as you wish, or let them fade as your mind settles. Infinity will remain, both in numbers and in realities, continuing its silent patterns, whether or not you choose to look. The night sky dazzles with bright stars and luminous galaxies, yet hidden among them are quieter actors, the faint, elusive dwarf galaxies. These systems are small, often containing only a few million stars, compared to the hundreds of billions in giants like the Milky Way. Many are so dim that even powerful telescopes struggle to detect them. Still, they are crucial threads in the universe's design, silent yet essential. Dwarf galaxies come in many forms. Some are irregular swarms of stars, scattered loosely without clear structure. Others resemble tiny elliptical systems, smooth and rounded but faint. Still, others are called ultra-diffuse galaxies, their stars so spread out that they are almost transparent. What unites them is their modest light. They are the faint embers of the cosmic fire, glowing weakly in the shadows of their larger companions. Despite their size, dwarfs play an outsized role in cosmic history. Many orbit larger galaxies as satellites, tugged by gravity into long dances that can last billions of years. Our own Milky Way hosts dozens of such companions, including the Magellanic Clouds, visible to the naked eye from the southern hemisphere. Some are being stretched into streams by the Milky Way's pull, their stars scattered like threads unraveling from a woven cloth. These small galaxies also hold vital clues about dark matter. Because they are faint and lightly populated with stars, their motions reveal the presence of hidden mass more clearly than in giant galaxies. By studying the way stars orbit within dwarfs, astronomers infer that dark matter dominates their interiors. In fact, dwarf galaxies are among the most dark matter-rich objects known. They act as magnifying glasses for the unseen, exposing the invisible scaffolding on which the cosmos is built. Infinity shows itself here not through overwhelming brightness, but through quiet persistence. The universe is not only composed of blazing giants, it is also composed of whispers, faint lights that would vanish if not carefully sought. Just as the cosmos stretches endlessly in scale, it also stretches endlessly in subtlety. Every dim companion, every fragile cluster, is part of a larger whole. There is something gentle in this thought. Grandeur does not always roar, sometimes it flickers softly. The smallest galaxies, often overlooked, are still part of the great cosmic pattern. Their faint light tells us that infinity is not only about what is grand, but also about what is hidden, waiting patiently to be noticed. As technology improves, astronomers continue to discover new dwarfs, tucked into the halos of larger galaxies or drifting alone in intergalactic space. Each discovery adds another piece to the puzzle of cosmic structure. Slowly, a picture emerges, a universe where even the faintest voices contribute to the chorus, where the quiet light of dwarfs helps reveal the deep architecture of everything. The next time you look at the stars, remember that beyond the bright points are countless dim companions, too small to catch your eye yet woven into the same fabric. In the endless story of space, even the faintest lights matter. Between galaxies lies a vastness that appears, at first glance, to be nothing at all. No suns burn there, no planets orbit, no clusters shine. It is space stripped of spectacle, an expanse of darkness stretching between islands of light. This intergalactic medium is so thin that a cubic meter may contain only a few atoms, scattered across distances that defy comprehension. To our senses, it would feel like pure absence, a void without form. Yet, emptiness is never truly empty. Even in the coldest reaches of space, particles drift. Hydrogen and helium float as faint traces of the early universe, stretched thin by billions of years of expansion. Clouds of gas wander between galaxies, invisible to human eyes but revealed in the way they absorb or bend light passing through them. In this darkness, astronomers detect whispers absorption lines in the spectra of distant quasars that reveal hidden reservoirs of matter. And beyond particles there is something subtler still, the restless murmur of the quantum vacuum. According to modern physics, space is never entirely still. Tiny fluctuations rise and fall even in apparent nothingness, momentary sparks that blink into being and vanish again. These fluctuations are invisible to us, but they remind us that the void is not absence but potential, a restless backdrop to everything. Cold defines these spaces too. Temperatures in intergalactic regions sink close to absolute zero. There is no warmth from nearby stars, no radiant heat from bustling galaxies. Only the faint afterglow of the Big Bang remains, stretched into microwave radiation that bathes the cosmos at a uniform chill of 2.7 degrees above absolute zero. This background hum fills even the emptiest reaches, a reminder that the universe still carries the memory of its fiery birth. Despite their bleakness, these voids are not irrelevant. They shape the arrangement of galaxies, carving the boundaries of the cosmic web. Matter flows away from emptiness and into filaments, guided by gravity. In this way, nothingness becomes architect. By being less, it allows structure to grow elsewhere. The cold and the empty are not failures of creation, but conditions that make creation possible. For us, such vast silences can be strangely reassuring. In a universe of explosive stars and dynamic galaxies, there is also room for stillness. These voids remind us that existence is not only about brightness and activity, but also about balance. The dark spaces between the lights give the lights their meaning, framing them like pauses frame words in a sentence. As you reflect on this, you may picture not a hostile vacuum but a quiet sea, calm and untroubled. It stretches outward in all directions, patient and undemanding. Galaxies are the islands scattered across it, but the sea itself is just as real. To know that the cosmos holds such stillness is to understand that even in the cold and the empty, there is order, presence, and quiet beauty. For centuries, gravity was imagined as an invisible tether, pulling objects together. Planets circled the sun, apples fell to the ground, tides rose and fell, all explained by this unseen force. Yet in the 20th century, Albert Einstein proposed a more intricate vision. Gravity, he suggested, is not a force transmitted across space, but the very shape of space itself. Massive objects bend space-time, and the bending tells other objects how to move. From this vision emerged an extraordinary prediction. When massive bodies accelerate, when stars collide or black holes spiral together, they should send ripples through space-time itself. These ripples are known as gravitational waves. For decades, gravitational waves were theory alone, too faint to detect with the instruments of the time. Imagine the surface of a pond. A pebble makes ripples easily seen, but if the pond were the size of the universe, even the fall of mountains might make waves so delicate they would be nearly invisible. That was the challenge facing scientists, to detect distortions in space-time far smaller than the width of a single atom. In 2015, After years of preparation, the Laser Interferometer Gravitational Wave Observatory finally succeeded. Twin observatories in the United States detected a passing tremor in space-time caused by the collision of two black holes more than 1 billion light-years away. The signal was brief, less than a second, yet within it lay confirmation of Einstein's vision. Space itself had stretched and compressed, and humanity had felt the movement. What makes gravitational waves remarkable is not only their existence but what they reveal. Light can be blocked, scattered, or absorbed, but gravitational waves pass through matter with ease. They carry unaltered stories of the most violent cosmic events, colliding black holes, merging neutron stars, perhaps even echoes from the earliest instants of the universe. They are messengers from places light cannot reach, whispers from regions otherwise hidden. To detect them, scientists built instruments of exquisite precision. Laser beams travel kilometers down long vacuum tubes, reflecting off mirrors suspended in isolation. When a wave passes, the distance between mirrors changes by less than a fraction of a proton's width, yet the lasers notice. It is like hearing the faint vibration of a string across the noise of a storm, delicate but unmistakable. The discovery of gravitational waves opened a new era of astronomy. Where once we relied only on light radio, infrared, visible, X-ray, we now listen to the universe through its vibrations. Already these detections have taught us about the population of black holes, the structure of neutron stars, and the ways galaxies grow through cosmic collisions. The universe is not silent after all. It hums and trembles, and we are learning to listen. There is a quiet wonder in knowing that even the emptiest stretches of space can carry waves. The cosmos is not rigid but elastic, able to ripple and ring like a vast, invisible drum. Each wave that reaches us carries not just information, but also reassurance that the laws of nature hold true across unimaginable distances. When you think of space, you may imagine stillness, a vast calm void. But hidden within that stillness are movements, subtle and profound. Gravitational waves remind us that the universe is alive with motion, that even space-time itself can sway and sing. To rest with that knowledge is to feel connected not just to stars and galaxies, but to the fabric of reality itself, stretching and vibrating gently, endlessly. For centuries, gravity was imagined as an invisible tether, pulling objects together. Planets circled the sun, apples fell to the ground, tides rose and fell, all explained by this unseen force. Yet in the 20th century, Albert Einstein proposed a more intricate vision. Gravity, he suggested, is not a force transmitted across space, but the very shape of space itself. Massive objects bend space-time, and the bending tells other objects how to move. From this vision emerged an extraordinary prediction. When massive bodies accelerate, when stars collide or black holes spiral together, they should send ripples through space-time itself. These ripples are known as gravitational waves. For decades, gravitational waves were theory alone, too faint to detect with the instruments of the time. Imagine the surface of a pond. A pebble makes ripples easily seen, but if the pond were the size of the universe, even the fall of mountains might make waves so delicate they would be nearly invisible. That was the challenge facing scientists, to detect distortions in space-time far smaller than the width of a single atom. In 2015, after years of preparation, the Laser Interferometer Gravitational Wave Observatory, LIGO, finally succeeded. Twin observatories in the United States detected a passing tremor in space-time, caused by the collision of two black holes more than 1 billion light-years away. The signal was brief, less than a second, yet within it lay confirmation of Einstein's vision. Space itself had stretched and compressed, and humanity had felt the movement. What makes gravitational waves remarkable is not only their existence but what they reveal. Light can be blocked, scattered, or absorbed, but gravitational waves pass through matter with ease. They carry unaltered stories of the most violent cosmic events, colliding black holes, merging neutron stars, perhaps even echoes from the earliest instants of the universe. They are messengers from places light cannot reach, whispers from regions otherwise hidden. To detect them, scientists built instruments of exquisite precision. Laser beams travel kilometers down long vacuum tubes, reflecting off mirrors suspended in isolation. When a wave passes, the distance between mirrors changes by less than a fraction of a proton's width. Yet the lasers notice. It is like hearing the faint vibration of a string across the noise of a storm, delicate but unmistakable. The discovery of gravitational waves opened a new era of astronomy, where once we relied only on light radio, infrared, visible, X-ray, we now listen to the universe through its vibrations. Already, these detections have taught us about the population of black holes, the structure of neutron stars, and the ways galaxies grow through cosmic collisions. The universe is not silent after all. It hums and trembles, and we are learning to listen. There is a quiet wonder in knowing that even the emptiest stretches of space can carry waves. The cosmos is not rigid but elastic, able to ripple and ring like a vast, invisible drum. Each wave that reaches us carries not just information, but also reassurance that the laws of nature hold true across unimaginable distances. When you think of space, you may imagine stillness, a vast, calm void, but hidden within that stillness are movements, subtle and profound. Gravitational waves remind us that the universe is alive with motion, that even space-time itself can sway and sing. To rest with that knowledge is to feel connected not just to stars and galaxies, but to the fabric of reality itself, stretching and vibrating gently, endlessly. The human sense of time is bound to days, months, and years. We measure by the turning of Earth, by the path of seasons, by the span of a lifetime. But the universe has its own clock, and its ticks are counted in billions of years. To step into a cosmic timeline is to stretch imagination across scales that far exceed anything familiar, to see history not as centuries but as epochs written into the fabric of space. The story begins nearly 13.8 billion years ago. In that first moment, the universe was dense and hot, a sea of energy unfolding into particles. Within minutes, the first atomic nuclei formed mostly hydrogen and helium, with traces of lithium. This was the era of nucleosynthesis, when the basic ingredients of all matter came into being. Hundreds of thousands of years later, atoms joined, and light finally streamed freely across space. That moment is preserved as the cosmic microwave background, the faint afterglow still visible today. The universe had cooled enough for clarity, the fog lifted, and transparency began. From there, hundreds of millions of quiet years followed. During this time, gravity worked in silence, drawing together regions that were slightly denser than their surroundings. Clouds collapsed, and the first stars kindled. These earliest stars were giants, short-lived and brilliant, forging heavier elements in their cores. When they died in explosions, they seeded the cosmos with the building blocks of new stars, galaxies, and eventually planets. Galaxies formed in webs, gathering into clusters, shaping the universe into its large-scale structure. Around 9 billion years ago, our Milky Way took form, a spiral swirled from gas, dust, and stars. Within one of its arms, about 4.6 billion years ago, a smaller story began. A cloud of gas collapsed, and in its center, the sun ignited. Around it, leftover material formed planets, moons, asteroids, and comets. Among those planets was Earth. On Earth, the cosmic timeline narrowed into something intimate. Within a few 100 million years, chemistry shifted into biology. Life appeared in simple forms, multiplying and adapting. Over eons, complexity grew. Cells joined into organisms, plants spread, animals diversified, and intelligence eventually emerged. Each step took millions of years, yet in the cosmic scale, it all happened in an eye blink. Our presence here is a recent development. If the history of the universe were compressed into a single calendar year, the Big Bang would occur on January 1st, the Milky Way would form in May, the Sun and Earth in early September. Life would arise in late September, dinosaurs in December, and humans only in the final minutes of December 31st. Civilization itself, the span of written history, would occupy only the last few seconds before midnight. Looking forward, the timeline stretches still farther. Stars will continue to form for billions of years, though at a slowing pace. Eventually, galaxies will age, stars will burn out, and new generations will dwindle. The universe may settle into cold and quiet, or perhaps into endings we do not yet understand. To trace these timelines is not to diminish human life, but to frame it. Our days and years are threads in a tapestry woven across billions of years. Knowing this can bring perspective, that our moment, however brief, is part of a vast story, connected to the first sparks of light and to futures that lie far beyond us. Astronomy is often described as the science of light. Every star, every galaxy, every distant quasar is known to us because of the light it has sent across space. Yet, even with the finest instruments, our ability to detect the universe is bounded. We are always peering through windows, limited by the sensitivity of our tools, the faintness of distant signals, and the unavoidable noise of the cosmos itself. At the heart of this challenge is the problem of scale. Light from a nearby star can be measured with ease, its brightness overwhelming even small telescopes. But when that same light must travel billions of years across an expanding universe, it arrives weakened, stretched, and easily lost in background glow. Detecting such signals requires extraordinary patience and precision. Observatories on Earth and in orbit are built to capture single photons at the edge of detectability, counting them one by one. Noise complicates the picture. Earth's own atmosphere blurs and absorbs light, hiding much of the infrared and ultraviolet spectrum. Radio signals from human technology spill into the sky, interfering with the faint whispers of galaxies. Even the detectors themselves produce noise, small random signals that mimic or mask the real. Astronomers must subtract, filter, and correct, teasing out genuine signals from layers of interference. There are also boundaries set by physics itself. The universe has an opaque past. Before 380,000 years after the Big Bang, light could not travel freely. No telescope can look beyond that curtain, because photons were trapped in a dense plasma. We glimpse earlier moments only indirectly, through gravitational waves or through mathematical reconstruction. Similarly, cosmic horizons mark distances from which light will never reach us, regardless of our instruments. Some mysteries are locked away not by technology, but by the nature of space-time. Yet boundaries are not barriers alone, they are also guides. Each limitation challenges scientists to invent new methods. Radio telescopes the size of cities trace the sky at long wavelengths. Space-based observatories escape atmospheric distortion. Interferometers link instruments across continents, creating resolution sharper than any single dish could achieve. The boundaries of detection expand whenever ingenuity finds a way to stretch them. The search for exoplanets illustrates this beautifully. Planets orbiting other stars are far too faint to see directly in most cases. Instead, astronomers detect them by watching for the tiniest dimming of a star's light as a planet passes in front, or by measuring the subtle wobble of a star tugged by a planet's gravity. These signals are vanishingly small, yet by patient accumulation, entire worlds are revealed, some rocky, some gaseous, some perhaps capable of harboring life. Boundaries remind us that science is an art of working with limits. We never see the universe in full. We see only what light and instruments allow. And yet, within those boundaries, entire histories are uncovered. A single photon captured on a sensor may tell of a star's birth, a galaxy's collision, or the expansion of space itself. There is calmness in this acceptance. We do not need to see everything to know that much lies beyond. Knowledge grows not by erasing limits, but by listening carefully to what lies within them. Boundaries are not endings. They are thresholds, marking the place where curiosity meets patience. And in that meeting, the universe reveals itself, slowly, delicately, but without fail. Let your attention settle gently. You do not have to follow every idea closely now. Think of this moment as setting your thoughts on a quiet shelf, leaving them there to rest. If drowsiness begins to gather, you may allow it to carry you away. If wakefulness lingers, that is perfectly fine too. There is no goal to reach, only the comfort of drifting with the rhythm of words. Amid all the grandeur of galaxies and the immensity of time, it is easy to imagine the universe as relentless. Yet even in its scale, there are pauses, intervals of calm where silence dominates. Astronomers call these places voids, vast regions between filaments of the cosmic web. They are expanses with few galaxies, stretching across hundreds of millions of light years. In their emptiness, they are restful. But a resting place is not only physical, it can also be intellectual. Science advances by pushing boundaries, but it also advances by pausing, by admitting what is not yet known. The unknown is not a failure, it is a landscape waiting for future journeys. Questions about dark matter, dark energy, the fate of time itself, remain open. In the quiet of those open questions lies a kind of peace. The human mind, too, needs pauses. We are not built to carry infinity all at once. Instead, we absorb it in pieces, like glimmers of starlight caught in intervals of darkness. To know that there are mysteries we cannot yet solve is freeing. It allows us to wonder without pressure, to marvel without needing to master. On a cosmic scale, resting places appear in other forms as well. Stars live dynamic lives, but between their outbursts, there are long stretches of steady fusion, quiet burning that lasts for billions of years. Galaxies, too, go through bursts of activity and long periods of calm. Even the universe itself experienced an era often called the Cosmic Dark Ages, a time after the first light of the Big Bang but before the first stars ignited. For hundreds of millions of years, space was filled with hydrogen, dark and waiting. Out of that pause, new brilliance emerged. These patterns remind us that stillness is not empty. Pauses are not voids in meaning, but fertile spaces where the next chapter prepares itself. Rest, in this sense, is part of creation. Without pauses, music would be noise. Without gaps, light could not be distinguished from shadow. Without moments of stillness, movement itself would lose significance. As you let your mind drift, think of yourself as part of this rhythm. You, too, belong to cycles of activity and rest, questions and silences, searching and pausing. Tonight is one of those pauses. It does not need to accomplish anything. It is simply a resting place in the vastness, a moment of calm amid the currents of existence. The universe holds both intensity and quiet. To notice the quiet is to find balance, to know that not all is motion, not all is expansion. There is room for silence, room for rest, room for peace, and in that recognition, you may allow yourself to rest as well. Among the endless stars scattered across the galaxy, only some worlds offer the conditions for life as we know it. These planets are often described as islands in a vast cosmic sea, rare pockets where chemistry, temperature, and stability combine in just the right way. To search for these islands is to ask where life might flourish beyond Earth, and what it takes to transform matter into something living. Astronomers begin this search with a simple guideline: distance from a star. Too close, and heat strips atmospheres, boiling away oceans. Too far, and water freezes solid, leaving barren landscapes. Between these extremes lies a region known as the habitable zone, sometimes called the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist. Water, the great solvent of life, is the first key in the search for habitable islands. Yet distance alone is not enough. A planet must also have the right size and composition. Too small, and it cannot hold on to an atmosphere. Too large, and it may become a gas giant with crushing pressures. Magnetic fields help protect surfaces from radiation. Geological activity recycles elements and stabilizes climates. Each of these factors adds complexity, narrowing the chances for life but also highlighting the remarkable balance Earth has achieved. In recent decades, telescopes have revealed thousands of exoplanets orbiting distant stars. Some are hot giants skimming the edges of their suns, others are frozen spheres circling dim embers, but sprinkled among them are planets that resemble Earth in size and orbit, potential harbors for life. They are the most exciting discoveries, glimpses of possible islands in a sea otherwise dominated by extremes. The search does not stop at planets. Moons may also hold promise. In our own solar system, Europa and Enceladus, moons of Jupiter and Saturn, conceal oceans beneath their icy crusts. Tidal forces from their parent planets keep these waters liquid, offering hidden seas that may support microbial life. Here, habitability is not about distance from the sun, but about the quiet heating of gravitational pulls, creating conditions far from the classical Goldilocks zone. The image of habitable islands carries comfort as well as wonder. In the vastness of the cosmos, life may not be everywhere, but it may not be singular either. Just as the Earth is not the only planet, perhaps it is not the only shore where living chemistry took root. The ocean of stars is wide, but islands may be scattered across it, waiting to be found. Still, there is humility in this search. Even if habitable planets abound, the leap from chemistry to biology is uncertain. The origin of life remains one of science's greatest mysteries, a transformation we do not yet fully understand. Some islands may remain barren despite favorable conditions. Others may host forms of life, unlike anything we can imagine. Whether rare or common, habitable islands remind us of fragility. Earth itself is one such island, a unique oasis amid endless space. Its oceans, atmosphere, and balance of conditions are gifts of circumstance. To recognize that is to see the value of care, the importance of sustaining the one island we already know. So when we imagine other worlds, scattered like pearls in the cosmic sea, we also remember our own. The search outward teaches us something inward, that every habitable island is precious, and that even in infinity, places of life are jewels beyond measure. When people gaze into the night sky, one question often arises. If the universe is filled with stars and planets, where is everyone? This puzzle is known as the Fermi paradox, the tension between the expectation that life should be common and the observation that we see no clear signs of it. The silence is profound. Across billions of galaxies, each holding billions of stars, not a single unambiguous signal has reached us. The paradox begins with numbers. Even if only a fraction of stars host planets, and only a fraction of those lie in habitable zones, the sheer scale suggests that many worlds should be suitable for life. If intelligent civilizations arise on even a small percentage, the galaxy should be sprinkled with them. Yet all our searches, listening for radio signals, scanning for megastructures, watching for unusual patterns, have yielded nothing but cosmic quiet. One explanation is that life itself is rare. The step from chemistry to biology may be so improbable that Earth is among the few places it has ever happened. Another possibility is that simple life is common, but complex, intelligent life is fragile, requiring conditions that seldom align. Planets may teem with microbes while never giving rise to civilizations capable of technology. There is also the idea of timing. Civilizations may emerge and fade in spans much shorter than cosmic time. If one appeared 1 billion years ago and vanished after 1,000,000 years, we might never know. The galaxy could host a sequence of sparks, each burning briefly before going dark, too scattered to overlap. From our perspective, the result would still be silence. Some imagine barriers, what scientists call great filters, that prevent civilizations from advancing far. Perhaps self-destruction, environmental collapse, or other limits curb technological growth before it can spread across the stars. If such filters exist, they may lie behind us, already past, or ahead of us, waiting still. The silence leaves both possibilities open. Others suggest that the silence is not absence but distance. Signals weaken as they travel, and civilizations may not send out powerful beacons. Communication across hundreds or thousands of light years requires patience measured in centuries. Perhaps messages are already on their way, but we will not receive them for generations to come. There are even more speculative answers, that advanced civilizations may choose not to reveal themselves, preferring quiet observation, or that their technologies are so different from ours that we would not recognize their signals even if we saw them. The silence, in this view, is not empty but misunderstood. Yet, the silence has its own beauty. It grants us perspective. If we are rare, then our responsibility to sustain life grows even greater. If we are not rare, then we are part of a larger community we have yet to meet. In either case, the quiet sky is not a disappointment, but an invitation to listen carefully, to cherish the life we know, and to prepare for discoveries still ahead. The stars above remain steady, each a possible home. The absence of voices does not mean the sea of space is empty. it only means the search continues. The great silence is not the end of the story. It is the space between questions and answers, between expectation and discovery. And in that space, possibilities remain as countless as the stars themselves. Stars, galaxies, and planets may seem eternal to us, but each has a lifespan. The cosmos is dynamic, filled with cycles of creation and decay. Yet there is also a striking resilience woven into its structure, forms of durability that stretch across billions of years. To think about cosmic longevity is to glimpse time not as fleeting, but as an almost unshakable endurance. Begin with stars. Their lives depend on mass. Small stars, called red dwarfs, burn their fuel slowly and steadily. They may shine for trillions of years longer than the universe has yet existed. Compared to our Sun, which will live for about 10 billion years, these dwarfs are paragons of patience. They fuse hydrogen so cautiously that they waste little, glowing faintly but persistently. Long after brighter stars fade, red dwarfs will still be shining, guardians of the deep future. Larger stars are less durable. They blaze with intensity, consuming their fuel rapidly. Some live only a few million years, a brief moment in cosmic terms. Their deaths are spectacular supernovae that scatter heavy elements into space. Yet even these violent endings serve durability, for the elements released build future stars, planets, and life. Through death, resilience continues. Galaxies, too, display endurance. The Milky Way has existed for more than 13 billion years, surviving collisions, mergers, and internal reshaping. Galaxies are not static, but they persist as collections, held together by gravity and dark matter. Even when two galaxies collide, the result is not destruction but transformation, as stars and gas weave into new forms. Planets can also endure for billions of years if their orbits are stable. Earth has circled the Sun for more than 4 billion years, weathering asteroid impacts, climate shifts, and continental drift. Stability emerges not from lack of change, but from the ability to absorb change and continue. In this sense, durability is not about stasis, it is about persistence amid transformation. On longer scales, even atoms tell stories of resilience. The protons in your body are thought to be stable for at least 10 to the power of 34 years, so long that no decay has ever been observed. They have endured since the birth of the universe, traveling through stars, dust, oceans, and cells, reshaped into countless forms, but never lost. Cosmic durability is not only vast, it is intimate, present in the matter that composes you. Yet nothing lasts forever. Even the most patient red dwarfs will eventually exhaust their fuel. Galaxies will thin as stars fade. Protons themselves may decay if certain theories are correct. The universe, as far as we can tell, tends toward dispersal, toward lower energy, toward stillness. Durability stretches far, but not infinitely. Still, there is peace in knowing that resilience is real and long-lasting, even if not eternal. The cosmos holds within it both impermanence and durability, and it balances the two across scales far beyond our own. For us, these vast spans can be a source of comfort. The Sun will shine for another 5 billion years. The Milky Way will continue for many more. Stars will still burn when every trace of human history has faded. To rest in that knowledge is to see durability as a kind of background harmony, steady, patient, and reassuring. The universe changes constantly, but it also endures. And within that endurance, there is room for life, for history, and for quiet reflection under the stars. As we continue this journey, you may notice your mind growing softer, less focused on details. That is welcome. You don't need to hold on tightly now. Let thoughts wander as they will, like a vessel drifting on calm waters. If sleep begins to rise, allow it to carry you forward. If not, you can rest, simply by listening. For humanity, knowledge has always been a way of finding direction. Long before telescopes and satellites, people looked to the stars to guide their paths across land and sea. Constellations became maps, the rising and setting of celestial patterns a calendar. The sky was both a storybook and a compass. In learning to read it, people learned to move with confidence through the unknown. In modern science, the idea of knowledge as navigation continues. We cannot travel across the cosmos, but we can chart it with observations. Redshifts trace the distances of galaxies. Gravitational waves reveal collisions of massive objects. The cosmic microwave background maps the universe's earliest conditions. Each discovery is a star on our intellectual compass, a fixed point by which we orient ourselves. Knowledge is not only about facts, it is also about direction, knowing where to look, which questions to pursue, which mysteries to let rest for now. Science moves forward through choices, like a ship deciding its course. Not every path can be followed at once. By navigating carefully, progress accumulates, and the unknown gradually becomes familiar. The act of navigation also acknowledges uncertainty. A sailor may not see the entire ocean, only the portion around the vessel. Likewise, astronomers see only the observable universe, a finite sphere defined by time and light. Beyond it lies more, perhaps infinitely more, but for now, our maps can only extend to the edge of visibility. This does not diminish knowledge, it frames it. A chart with edges is still a chart, useful and meaningful. There is humility in navigation, because it requires admitting that the journey is never complete. Every new observation may shift the course, every new idea may adjust the map. What matters is not reaching a final destination but continuing to move, guided by curiosity and care. Knowledge is not a finished library but a set of evolving directions, helping us travel through mystery with steadiness. And there is comfort, too, in realizing that maps need not be perfect to be useful. Ancient sailors navigated with rough charts and stories, yet they reached distant shores. In the same way, our cosmic maps, though incomplete, already reveal a universe filled with structure, beauty, and depth. They show us where we are, not in detail but in essence. On a small planet in the arm of a spiral galaxy, within a web of galaxies, inside an expanding universe. As you listen now, you don't need to memorize these details. Instead, think of knowledge as a lantern, shedding light just far enough for the next step. You don't need to see the whole path to move forward. You only need to trust the glow that guides you, and with each lantern we light each piece of knowledge gained, the cosmos becomes a little less dark, a little more navigable, and a little more familiar. When we speak of the universe, we often focus on beginnings, the Big Bang, the birth of stars, the rise of galaxies. But every beginning invites a question about endings. How will the cosmos conclude? Does it fade gently, collapse violently, or cycle endlessly? Scientists cannot yet give a final answer, but they have outlined several possibilities, each rooted in the laws of physics and the evidence we gather from the skies. One scenario is sometimes called the heat death. In this picture, the universe continues to expand forever. Stars burn their fuel, galaxies drift apart, and over unimaginable stretches of time, energy spreads thin. As the last stars fade, the cosmos becomes colder and darker, a place of sparse particles and low energy. It would not end in a sudden catastrophe, but in quiet dispersal, a slow slide into silence. This outcome is consistent with the presence of dark energy, which drives acceleration and ensures that expansion never reverses. Another possibility is the Big Rip. If dark energy is not constant but grows stronger over time, the expansion could accelerate without bound. Galaxies would separate first, then stars from their planets, then atoms themselves pulled apart by the relentless stretching of space. This is the most dramatic of the proposed endings, a universe unstitched at every scale. The evidence for it is uncertain, but the mathematics shows it could happen if dark energy behaves in particular ways. A different path is the Big Crunch. If expansion were someday to slow and reverse, gravity could pull everything back together. Galaxies would approach, stars would collide, and in the end, all matter and energy would compress into a dense state again, not unlike the beginning. This scenario has lost favor as evidence mounts for accelerating expansion, but it remains an elegant possibility. Some versions even suggest a cycle, a universe that expands, collapses, and expands again, in an endless rhythm of births and deaths. There are also subtler endings. Black holes may dominate the far future, swallowing stars and matter until only radiation leaks from their slow evaporation. In this view, The universe could pass through an era of black holes lasting far longer than the current age, before even those giants fade. On smaller scales, protons themselves might eventually decay, dissolving matter into a thin mist of particles. These processes would unfold on timescales beyond imagination, trillions upon trillions of years. For us, what matters is not which ending is correct, none are close enough to touch us, but what they reveal about the nature of reality. They remind us that the universe is dynamic, that even the largest structures evolve, that permanence is an illusion. Yet there is calm in this recognition too. Just as stars live and die, galaxies form and change, so too does the universe itself. To see it as a story with possible endings is not frightening, but natural. We cannot choose which scenario will unfold. What we can do is marvel that we are here, now, in the middle of the story. We are witnesses to a universe still full of light, still rich with galaxies, still echoing with the energy of its beginning. The endings, whatever they may be, lie far beyond our time. For us, the present is enough. A moment of brilliance in a cosmos that will continue to transform long after we are gone. When we imagine the universe, it is easy to think of space and time as separate. Space stretches outward in 3 dimensions, while time ticks forward as a steady beat. Yet modern physics shows us that they are not separate threads but woven together into a single fabric, space-time. This fabric bends, curves and ripples, and in its patterns the story of the cosmos is written. Think of a tapestry stretched across a loom. Each thread has its place, but meaning emerges only when they intertwine. In space-time, events are the woven points, moments where space and time intersect. A star forming, a planet circling, a person breathing, all are threads in the same cloth. We live not beside space-time but within it, inseparable from the weave. Einstein's theory of relativity revealed that space-time is dynamic, not static. Massive objects, such as stars and galaxies, curve it, creating valleys into which smaller objects fall. Time itself is affected. A clock on a mountain runs slightly faster than one in a valley, because gravity shapes not only space but also the passage of seconds. To move through the cosmos is to move across a landscape of curved time as well as curved space. The imagery of fabric is not only poetic, it is practical. Astronomers use it to visualize gravitational lensing, where light bends around massive objects. They use it to understand the spiraling dance of binary stars, which ripple space-time with gravitational waves. They use it to frame the possibility of black holes, regions where the fabric folds so steeply that nothing can climb back out. Each of these is a thread in the larger story. But a tapestry is not woven only once. It is added to continuously, thread by thread. Space-time, too, is still unfolding. With every second, more of the pattern comes into being. Galaxies drift farther apart, stars live and die, planets turn, and life reflects on its place in the whole. What we call the present is not a fixed point but a moving edge of the weave, where new threads are added to the pattern of existence. Stories emerge naturally from this view. When you trace the path of a photon from a star to your eye, you are following a thread through space-time. When you chart the evolution of Earth, from its fiery beginnings to its blue oceans, you are describing a section of the tapestry. Even your own life, with its moments of change and memory, is a sequence of threads stitched into the larger cloth. This perspective is quietly humbling. The universe is not only vast in size but also rich in narrative. Every event, no matter how small, is part of the pattern. You may never see the whole design, but you can know that it exists and that you are woven into it. The tapestry is not finished, and perhaps it never will be. Its weave stretches outward in all directions, carrying stories of past, present, and future. To rest with this image is to see yourself not as separate from the cosmos, but as a strand within it, delicate yet essential, part of a design that spans the very fabric of reality. In the sweep of galaxies and the immensity of time, Earth may appear small, even fragile, yet it is here, on this pale blue sphere, that every story of life has unfolded. Against the backdrop of the infinite, Earth is not diminished but distinguished, an island of color and complexity in a sea of darkness. To see Earth in its cosmic context is to recognize both its rarity and its meaning. From space, our planet reveals itself as a sphere of oceans and clouds, continents and ice. Astronauts often speak of the overview effect, a shift in perception that comes from seeing Earth without borders, suspended in the blackness of space. From that vantage, politics and divisions fade, and what remains is the clarity of a single home, shared by all who live upon it. The ingredients that make Earth habitable are not extraordinary in isolation. Water, an atmosphere, moderate warmth from the Sunday, but the combination, balanced over billions of years, is astonishing. The magnetic field shields life from harmful radiation. Plate tectonics recycle minerals and regulate climate. The tilt of Earth's axis gives rise to seasons, fostering diversity. Each factor is a thread, and together they weave the living fabric of the biosphere. Earth has endured change. Ice ages have come and gone. Continents have shifted, oceans opened and closed. Species have flourished and vanished. Through all of it, the planet has remained resilient, sustaining life in many forms. This adaptability is part of what makes Earth remarkable. Not unchanging perfection, but the capacity to host change while still nurturing life. Placed in the context of the wider universe, Earth reminds us of perspective. Billions of planets may exist, and some may be habitable. Yet for us, here and now, Earth is the only one we know intimately, the only one that has given rise to forests, oceans, and human thought. Our search for other habitable worlds is not a dismissal of Earth, but a reflection of how precious and rare such worlds may be. The recognition of Earth as a cosmic home also carries responsibility. Fragility is part of its beauty. Its atmosphere is a thin veil, its ecosystems delicately balanced. To protect Earth is not only practical but also an act of gratitude, an acknowledgement that we live on a rare island in a vast and often hostile universe. At the same time, this perspective offers comfort. Against the immensity of galaxies and the cold reaches of space, we are not lost, we are anchored. Earth gives us orientation, a place where the story of the universe has become personal. Its rivers and skies, its stones and soils, are part of a much larger narrative, but they are also the ground beneath our feet. So when you look outward into the depths of space, remember also to look inward, toward the ground you stand on. The cosmos is open and vast, but Earth is the place where that vastness becomes experience, where matter has become memory, and where the universe has given itself the shape of home. On Earth, measurement begins with anchors. We stretch rulers against objects, count seconds on clocks, weigh matter with scales. Every measure is tied to something fixed and familiar. But in the cosmos, there are no anchors. There is no absolute ruler laid across space, no universal clock ticking in the background. To measure in astronomy is to work without fixed reference points, to find order amid motion and distance. The challenge begins with size. How far away is a star? Light gives us clues, but distance itself is not directly visible. Astronomers rely on parallax, the apparent shift in a star's position against distant backgrounds as Earth moves around the Sunday. From this tiny motion, measured in fractions of degrees, distances to nearby stars can be deduced. For farther stars, other methods take over. Brightness compared to known standards, redshifts in spectral lines, or the timing of supernovae. Each method is a step in a ladder, reaching farther outward. Time poses its own puzzles. The universe does not provide a master clock. Instead, astronomers turn to processes as natural timekeepers. The decay of radioactive elements reveals ages of rocks and planets. The cooling of white dwarf stars tells how long they have glowed. Even the faint cosmic microwave background acts as a kind of clock, a record of conditions 13.8 billion years ago. Each is not a clock in itself, but a rhythm we interpret as time. Measurement without anchors requires creativity. The kilogram is defined by a platinum cylinder stored on Earth, the meter by the speed of light in a vacuum. But beyond Earth, nothing remains fixed. Galaxies move away from one another. Space itself expands. Even the constants of physics, though believed unchanging, are tested again and again to confirm their stability. Science thrives by finding patterns that hold even when anchors drift. The metaphor of navigation fits here. Imagine steering a vessel without landmarks, guided only by stars whose positions change with the seasons. Each observation must be combined with others to create a chart, a framework that grows more accurate over time. Astronomers work in this way, piecing together distances, velocities, and ages, not because any one measure is absolute, but because together they form a coherent picture. This approach reveals something profound, that knowledge is built not from certainties, but from consistency. Each method, each estimate, is cross-checked against others. Parallax confirms stellar brightness. Brightness confirms redshift. Redshift confirms expansion. The web of consistency gives confidence where no anchor exists. There is humility in this art. To measure the cosmos is not to grasp it completely, but to map what can be mapped, to accept uncertainty at the edges. Boundaries of error are not flaws, but acknowledgements of reality. Even so, the results are astonishing. Ages of galaxies, sizes of planets, trajectories of stars, all traced without ever leaving Earth. For us, the lesson is broader. Life, too, is often lived without fixed anchors. We navigate with shifting references, memories, hopes, relationships, seasons. Certainty is rare, but patterns can guide us. Just as astronomers build meaning from consistency, we build meaning from coherence, finding direction without absolute markers. The universe does not provide a ruler across the stars, yet we measure. It does not give us a universal clock, yet we keep time. Knowledge grows not because anchors exist, but because curiosity finds ways to move without them. And in that art of measuring without anchors, the cosmos becomes legible, even in its vast and shifting expanse. On Earth, measurement begins with anchors. We stretch rulers against objects, count seconds on clocks, weigh matter with scales. Every measure is tied to something fixed and familiar. But in the cosmos, there are no anchors. There is no absolute ruler laid across space, no universal clock ticking in the background. To measure in astronomy is to work without fixed reference points, to find order amid motion and distance. The challenge begins with size. How far away is a star? Light gives us clues, but distance itself is not directly visible. Astronomers rely on parallax, the apparent shift in a star's position against distant backgrounds as Earth moves around the sunday. From this tiny motion, measured in fractions of degrees, distances to nearby stars can be deduced. For farther stars, other methods take over. Brightness, compared to known standards, redshifts in spectral lines, or the timing of supernovae. Each method is a step in a ladder, reaching farther outward. Time poses its own puzzles. The universe does not provide a master clock. Instead, astronomers turn to processes as natural timekeepers. The decay of radioactive elements reveals ages of rocks and planets. The cooling of white dwarf stars tells how long they have glowed. Even the faint cosmic microwave background acts as a kind of clock, a record of conditions 13.8 billion years ago. Each is not a clock in itself, but a rhythm we interpret as time. Measurement without anchors requires creativity. The kilogram is defined by a platinum cylinder stored on Earth, the meter by the speed of light in a vacuum. But beyond Earth, nothing remains fixed. Galaxies move away from one another. Space itself expands. Even the constants of physics, though believed unchanging, are tested again and again to confirm their stability. Science thrives by finding patterns that hold even when anchors drift. The metaphor of navigation fits here. Imagine steering a vessel without landmarks, guided only by stars whose positions change with the seasons. Each observation must be combined with others to create a chart, a framework that grows more accurate over time. Astronomers work in this way, piecing together distances, velocities, and ages, not because any one measure is absolute, but because together they form a coherent picture. This approach reveals something profound, that knowledge is built not from certainties, but from consistency. Each method, each estimate, is cross-checked against others. Parallax confirms stellar brightness. Brightness confirms redshift. Redshift confirms expansion. The web of consistency gives confidence where no anchor exists. There is humility in this art. To measure the cosmos is not to grasp it completely, but to map what can be mapped, to accept uncertainty at the edges. Boundaries of error are not flaws, but acknowledgements of reality. Even so, the results are astonishing. Ages of galaxies, sizes of planets, trajectories of stars, all traced without ever leaving Earth. For us, the lesson is broader. Life, too, is often lived without fixed anchors. We navigate with shifting references, memories, hopes, relationships, seasons. Certainty is rare, but patterns can guide us. Just as astronomers build meaning from consistency, we build meaning from coherence, finding direction without absolute markers. The universe does not provide a ruler across the stars, yet we measure. It does not give us a universal clock, yet we keep time. Knowledge grows not because anchors exist, but because curiosity finds ways to move without them. And in that art of measuring without anchors, the cosmos becomes legible, even in its vast and shifting expanse. You may notice by now that the words are slowing, and that your own thoughts may be softening with them. This is not a lecture to remember, but a rhythm to rest within. If sleep begins to arrive, welcome it as you would a quiet guest. If it does not, you are still resting, still carried gently by ideas, meant to soothe as much as inform. In astronomy, horizons are not edges of land, but boundaries of what can be known. The event horizon of a black hole marks the point beyond which no light escapes. The cosmic horizon defines how far we can see, limited by the age of the universe and the speed of light. These horizons are not walls, they are limits to perspective. Beyond them, events may unfold, but their signals will never reach us. There is something calming in recognizing such limits. The universe is vast, yet even it has boundaries of observation. What lies beyond is not for us, at least not now. The horizons remind us that knowledge does not have to be complete to be meaningful. We are permitted to rest at the edges, to pause where vision stops, and still find wonder in what we can see. Horizons also create contrast. They frame what lies within. Just as the line of a horizon on Earth divides sky from ground, cosmic horizons divide the known from the unknown. They remind us that mystery is part of the landscape, that silence and distance have their place alongside discovery. For the human mind, horizons can serve as metaphors for rest. Each day has its edge, where work ends and sleep begins. Each thought has its boundary, beyond which lies quiet. We do not need to push beyond every limit. Sometimes the most meaningful act is to stop at the horizon, to acknowledge its presence, and to let stillness take over. In cosmic terms, horizons are dynamic. As the universe ages, the particle horizon grows. Light from ever more distant galaxies has had time to reach us. Yet the event horizon, shaped by dark energy, shrinks our accessible future, sealing away galaxies that accelerate beyond contact. Horizons shift, but they remain. They are companions to expansion, always present, always marking the line between reach and silence. Perhaps the greatest gift of horizons is perspective. They remind us that seeing everything is not required. To live within partial vision is natural, even beautiful. The night sky we admire is itself bounded, yet within those bounds lies enough to inspire centuries of wonder. Completeness is not necessary for meaning. As you settle further into rest, think of horizons not as barriers but as invitations to pause. Beyond them lies mystery, but here, within them, lies enough. Stars, galaxies, histories of light, all offered within our view. Beyond that, silence. Both are part of the whole. If your mind is still awake, you may hold the thought that every horizon, whether cosmic or personal, marks a transition into rest. If sleep has already come, the horizon has done its work, closing the day and opening the quiet that follows. When we seek to describe the universe, words often fall short. Human language is shaped by daily life, by the scales of minutes, meters, and memories. But the cosmos operates on scales so vast and in patterns so subtle that ordinary speech stumbles. What emerges instead is mathematics, a language not spoken but written in symbols, equations, and relationships. It is through this language that the universe becomes legible. Mathematics has a peculiar quality. It is abstract, yet astonishingly effective at describing reality. The orbit of planets can be captured in a few lines of geometry. The growth of galaxies emerges from equations of gravity. The ripples of gravitational waves match predictions made a century earlier with uncanny precision. These are not coincidences, but reflections of a deeper truth that mathematics is the structure behind the phenomena. Some thinkers describe mathematics as discovered, like continents waiting on a map. Others see it as invented, a creation of human minds refined over centuries. Yet whether discovered or invented, it works. Numbers, ratios, and symmetries allow us to predict eclipses, to design telescopes, to model the birth of the universe itself. Mathematics becomes the bridge between imagination and observation. Patterns are at the heart of this language. Nature speaks in repetition and symmetry. Snowflakes crystallize with hexagonal precision. Spirals echo in galaxies and seashells alike. Ratios that govern harmonies in music also appear in orbital mechanics. Each pattern is a phrase, and together they compose a grammar of reality. To learn mathematics is to learn to read these phrases with clarity. At cosmic scales, mathematics takes us where no instrument can reach. Equations model the first instance of the Big Bang, long before light existed. Probabilities sketch the quantum world, where certainty dissolves but patterns remain. Even the possibilities of other universes, beyond detection, arise not from observation but from the internal logic of equations extended beyond what we can test. The precision of mathematics also reveals beauty. There is elegance in an equation that captures complexity in a simple form, like Einstein's E equals mc squared or Newton's laws of motion. These symbols condense vast truths into compact expressions, like poetry stripped of ornament but rich in meaning. To see such equations is to glimpse the skeleton of reality itself, and yet, mathematics is not cold or distant. It is alive with creativity. Mathematicians explore new structures, much as artists explore new forms. Sometimes these structures later turn out to describe physical phenomena. Imaginary numbers, once a curiosity, became essential in quantum mechanics. Geometry developed for beauty alone became the framework for relativity. What begins as abstract play can reveal the shape of the universe. For us, mathematics as a cosmic language teaches humility and connection. Humility, because it shows that the universe speaks in a tongue far older and wider than our own. Connection, because by learning this tongue, we align ourselves with the patterns of reality. The symbols on a page are not mere marks, they are echoes of galaxies, stars, and the very structure of space-time. So when you hear of equations describing black holes or constants governing light, you may think of them not as puzzles but as sentences in the language of the cosmos. To read them is to listen to the universe speaking. And even if you do not master the symbols, you can rest in the assurance that the cosmos has a grammar and that mathematics is the voice through which it quietly tells its story. The universe has no bookshelves, no written archives stored on parchment or stone, yet it carries its own memory, preserved in light, in matter, and in structure. Every photon, every atom, every distribution of galaxies is part of a record, an account of what has happened since the beginning. To study the cosmos is to read these records, not in words, but in signals imprinted across space and time. The most ancient memory is the cosmic microwave background. It is the afterglow of the Big Bang, released when the universe was only 380,000 years old. Before that time, light could not travel freely. It was trapped in dense plasma. But when atoms formed, light escaped, filling the universe with a faint glow. That glow still exists, stretched into microwaves by billions of years of expansion. It is a perfect record of conditions in the early universe, a photograph of the cosmos as an infant. Galaxies, too, act as archives. Their shapes tell stories of collisions and mergers. Spirals carry evidence of steady star formation. Ellipticals, rounded and smooth, reveal violent pasts where smaller galaxies combined. Star clusters record the chemistry of their birth clouds, locking into their atmospheres the abundances of elements forged by earlier generations of stars. Each galaxy is a chapter written in structure and motion. Stars themselves are keepers of history. By analyzing their spectra, astronomers learn not only their present composition but also the legacy of earlier stars. Heavy elements like iron or gold were not born in the stars we see now, but in older ones that exploded long ago. Those explosions scattered material that later became part of new stars, planets, and even our own bodies. To read a star's spectrum is to glimpse a record of ancestry reaching back across billions of years. On smaller scales, planets and moons preserve memory in their surfaces. Craters on the moon tell of impacts that shaped the early solar system. Rocks on Earth carry isotopes that reveal ages and processes. Ice cores hold bubbles of ancient atmosphere, keeping records of climates long past. Even here, in the material beneath our feet, the cosmos leaves its marks. But the deepest memory is in light itself. Every photon travels as a messenger, preserving the conditions of its origin. When we observe distant galaxies, we see them not as they are now, but as they were when the light left them. In this way, the night sky is not the present, it is a mosaic of past moments. Each star is a time capsule, each glimmer a memory of an earlier state of the universe. This perspective changes how we think about now. The present moment is not a single instant, but a convergence of records. Light from the sun, only 8 minutes old. Light from Andromeda, millions of years old. Light from galaxies, billions of years old. When you look up, you are not seeing one time, but many, layered together like pages scattered across the sky. Cosmic memory teaches patience. The universe does not hurry to record itself, but every event leaves traces. Some are bright and obvious, others are faint and require great care to detect. Yet nothing is entirely lost. Even silence carries meaning, for gaps in data tell of horizons beyond which signals cannot reach. To rest in this awareness is to know that the universe remembers itself, and that in studying it, we join in the act of remembering. We are both readers and part of the record, for our own existence is one more page in the story, written not in ink but in atoms, light, and time. When we consider the universe, it is tempting to search for inevitability patterns that could not have been otherwise, laws that guarantee outcomes. Yet side by side with necessity runs chance, a current of accidents shaping the cosmos in ways both subtle and profound. The universe is not purely ordered nor purely random, it is a dialogue between the two, where structure emerges from rules and variation emerges from circumstance. Physics gives us necessity, gravity pulls with unfailing consistency, light travels at a fixed speed, atoms follow predictable rules of quantum mechanics. These are the foundations on which the cosmos is built. Without them, stars would not shine, planets would not form, and life would not be possible. Necessity is the skeleton of the universe, holding everything together with reliable strength. But within that framework, accidents play their part. The exact distribution of matter after the Big Bang contained tiny irregularities, slight fluctuations in density. Had those fluctuations been different, galaxies might not have formed in the same way, or perhaps not at all. The structure we see now owes its existence to the particular pattern of those early variations, accidents frozen into the fabric of space. On smaller scales, accidents shape stars and planets. A giant cloud of gas may collapse into one star or fragment into many, depending on subtle variations in turbulence and temperature. A planet's orbit may remain stable for billions of years, or shift dramatically after a close encounter with another body. Even the impact that likely created Earth's moon, a collision between our young planet and a Mars-sized object, was an accident, one outcome among countless possibilities. Yet from that event came tides, stabilized seasons, and conditions favorable to life. Life itself embodies this interplay. The chemistry that gave rise to the first living cells may have been a rare accident, yet once established, the rules of evolution guided its diversification. Mutations arise by chance, but natural selection acts with necessity, favoring what endures. Across billions of years, accident and law together produce the variety of species we see today. Astronomy teaches us that chance does not mean chaos. Accidents are shaped by context. A roll of dice produces randomness, but only within the rules that define the dice. In the same way, cosmic accidents unfold within the boundaries set by physics. They do not break the laws, they explore the possibilities allowed by them. For us, this perspective is both humbling and liberating. Humbling, because it reminds us that our existence rests on contingencies, collisions that could have gone differently, fluctuations that might have taken another form. Liberating, because it shows that meaning need not require inevitability. Beauty can arise from a blend of rule and chance, from necessity holding the frame and accident filling it with color. The night sky, then, is not only a display of laws in action but also a record of contingencies. Each star, each galaxy, is both necessary and accidental, shaped by unchanging physics and unique circumstances. Together, they form the cosmos we inhabit, ordered enough to be understood, varied enough to be endlessly surprising. To rest in this thought is to see the universe as both secure and open. The laws will not fail, but the outcomes will never repeat exactly. Each moment, each pattern, is a singular balance of necessity and accident, and in that balance, the story of the cosmos unfolds. Human senses evolved for familiar ranges, distances we can walk, objects we can hold, times we can remember. Beyond those ranges, intuition falters. The cosmos, however, operates on scales so vast and so small that ordinary experience cannot prepare us. To enter its dimensions is to move beyond intuition into realms that stretch imagination to its limits. Start with distance. The Earth's circumference is about 40,000 kilometers. That seems immense when we travel across continents or oceans. Yet light, moving at 300,000 kilometers per second, circles the Earth 7 times in a single second. The Moon lies only a little over a second away by light. The Sun is 8 minutes away. The nearest star beyond the Sun, Proxima Centauri, is more than 4 years away by light. Already, intuition strains. Distances no longer feel like travel, they feel like abstractions. Expand further. The Milky Way spans about 100,000 light-years. To cross it, even at the speed of light, would take longer than the entirety of human history many times over. And the Milky Way is just one of hundreds of billions of galaxies. The observable universe itself stretches more than 90 billion light-years across, though it is only 13.8 billion years old, because space has been expanding throughout its history. At this point, numbers lose their grip. Scales outpace intuition entirely. Size is not only vastness but minuteness. Atoms, the building blocks of matter, are far smaller than we can see. Within them, protons and neutrons, and within those, quarks. The sizes shrink until comparison becomes meaningless. If an atom were enlarged to the size of a cathedral, its nucleus would be a grain of rice in the center. Most of what we call solid matter is emptiness filled with forces. The small is as counterintuitive as the large. Time, too, extends beyond intuition. Human lives span decades, civilizations span millennia. But stars live for billions of years, galaxies evolve for tens of billions, and the universe itself may continue for trillions. On the other end, quantum events occur in billionths of a second. To imagine both extremes at once, the near instant and the near eternal, is to realize how narrow our natural sense of time truly is. Astronomy, then, is an exercise in stretching the mind. Telescopes and equations are not just tools, they are extensions of thought, helping us reach scales otherwise inaccessible. Through them, we grasp numbers and relationships we cannot picture directly. We cannot see a billion light-years in our minds, but we can trace the faint galaxies that prove its reality. There is humility in confronting these scales. They remind us that intuition, though useful for daily life, is not the measure of all things. The cosmos is not obliged to fit within our comfort, and yet this does not alienate us, it enriches us. To learn of scales beyond intuition is to expand awareness, to accept that reality is larger and smaller, slower and faster than anything we might expect. And there is comfort too. Even if we cannot feel these scales directly, we can know them. Numbers and images translate them into meaning. We can stand on Earth, under the stars, and realize that both the immense and the minute are part of the same whole, the same reality that holds us, even when it defies our natural sense. To rest with this thought is to embrace wonder without needing complete comprehension. The universe exceeds intuition, but it does not exclude us. We are participants in it, even if its true scales lie beyond our native grasp. In the vastness of the cosmos, change is constant. Stars are born, live, and die. Galaxies collide, merge, and form anew. Even matter itself flows through transformations, moving from one form to another across billions of years. The universe is not a straight line of events, but a rhythm of cycles, a pattern in which endings are not final, but seeds for beginnings. Consider stars. A cloud of gas collapses under gravity, igniting nuclear fusion in its core. For millions or billions of years, the star burns, balancing gravity with the outward pressure of light. Eventually, its fuel runs out. A small star fades into a white dwarf, cooling slowly into silence. A massive star explodes, scattering heavy elements into space. From those scattered remnants, new clouds form, ready to collapse again. The atoms in our bodies were once part of such cycles, born in stars long gone. Galaxies also live in cycles. Over billions of years, they grow by merging with one another, drawing in gas, forming waves of new stars, and then settling into calmer forms. Our own Milky Way is on course to merge with the Andromeda Galaxy in about 4 billion years. The result will not be destruction but transformation, a new, larger galaxy reshaped by the blending of two. The cycle of growth continues at scales far beyond our own lives. On still larger scales, some cosmologists imagine cycles for the universe itself. One idea is the oscillating universe, where expansion slows, reverses, and collapses in a big crunch, only to be followed by another big bang. Though current evidence favors eternal expansion, the possibility of cosmic cycles reflects a deep intuition that nature may favor rhythms, not finalities. Even if the universe does not repeat in this way, the idea shows how cycles frame our understanding of existence. Cycles also appear in subtler ways. Chemical elements circulate endlessly. Water on Earth evaporates, condenses, and falls again. Carbon moves through plants, animals, air, and rock. On planetary scales, climates shift between ice ages and warm periods. These cycles remind us that repetition and renewal are not only cosmic but also immediate, written into the processes that sustain life. There is comfort in these patterns. To see cycles is to see continuity. Death of a star becomes birth of a planet. Collapse becomes creation. Silence becomes new sound. The universe does not simply end things, it reuses, reshapes, and renews. Each cycle carries forward what came before, woven into something new. For human beings, cycles are also familiar. Days turn to nights, seasons return, generations succeed one another. Our lives follow rhythms, from heartbeat to breath, from learning to aging. To notice these patterns is to recognize that we are not separate from the universe's rhythms, we are part of them. Our cycles echo those of stars and galaxies, small reflections of larger processes. Cycles within eternity remind us that permanence is not required for meaning. Change is not loss when it is part of renewal. Endings can be understood as transitions, moments within a greater pattern. The universe does not cling to single forms. It allows them to pass, trusting that new forms will rise. As you rest with this thought, imagine the universe not as a straight road with an end, but as a great rhythm, pulsing across time. Stars flare, fade, and return as clouds. Galaxies weave together into new shapes. Even matter itself cycles through endless transformations. In this rhythm, eternity is not stillness, it is motion, repeating yet always new. The visible universe is dazzling stars, nebulae, galaxies glowing across the dark. Yet much of what shapes it is invisible, hidden beneath the surface of sight. The cosmos is built on an architecture that cannot be seen directly but reveals itself through its effects. To understand the universe is to learn to read these hidden structures, the frameworks that give form to what appears. One of the greatest mysteries is dark matter. Galaxies spin faster than their visible stars and gas should allow. If only ordinary matter were present, they would fly apart. Instead, an unseen mass provides the extra gravity needed to hold them together. This dark matter does not emit or absorb light, yet its presence is undeniable. It is like scaffolding, giving galaxies their shape and stability. Dark matter does more than hold galaxies in place. It forms vast halos, invisible cocoons within which galaxies form and evolve. On even larger scales, it shapes the cosmic web, the vast network of filaments and voids where galaxies cluster. Without this hidden substance, the universe would look very different, less structured, less connected. The visible stars are only the decoration. The architecture belongs to the unseen. Another hidden framework is dark energy. Discovered through observations of distant supernovae, it acts as a kind of pressure within space itself, driving the universe to expand faster and faster. Where dark matter pulls together, dark energy pushes apart. Together they account for about 95% of the universe, leaving ordinary matter, the stuff of stars, planets, and people, as a small remainder. The cosmos is ruled by what we cannot see. Even within the visible, hidden architectures appear. Symmetries underlie the laws of physics, quiet rules that dictate how particles interact and how forces behave. Conservation laws of energy, momentum, charge, are not obvious to the eye but frame every process we observe. Like the foundations of a building, they remain unseen while supporting everything above. The hidden architecture is also revealed through ripples. Gravitational waves, first detected in 2015, are distortions of space-time itself. They are not visible light but vibrations in the underlying fabric, telling us of black holes colliding, of neutron stars merging. These signals add to our awareness of a universe structured not only by what shines but also by what trembles and resonates beneath. To live in such a universe is to dwell among hidden companions. We move within halos of dark matter. We ride an expansion driven by dark energy. The atoms that compose us are shaped by symmetries we cannot touch. Our everyday experience is built atop frameworks both invisible and essential. There is humility in this recognition. The brightest objects, the stars we see each night, are only a fraction of reality. Much lies beneath, silent but powerful. The universe is not only what dazzles but also what sustains, unseen and enduring. And there is wonder too. To uncover hidden architectures is to expand perception. Instruments extend our senses, revealing what the eye alone cannot. Equations translate invisible rules into patterns we can understand. The cosmos becomes not only larger but richer, filled with layers of meaning beyond appearance. So when you look up at the night sky, remember that what you see is both real and incomplete. Behind the glittering lights lies scaffolding and energy, symmetries and ripples, and architecture vast and hidden, yet as real as the stars themselves. The universe is immense, filled with scales beyond measure, yet our encounter with it is deeply personal. Every glance at the night sky is filtered through human perception, our curiosity, our imagination, our capacity for awe. Science reveals distances and equations, but wonder turns those numbers into meaning. It is wonder that binds the human spirit to the cosmos, making the infinite feel intimate. From the earliest days, people looked upward, not only to navigate or mark seasons, but to ask questions. What are these lights? Where do they come from? Are we alone beneath them? These questions remain, though our answers grow more precise. Telescopes show galaxies where once there were only points of light. Spacecraft carry instruments beyond Earth's atmosphere. Still, behind every measurement is the same impulse. To wonder. Wonder thrives on contrast. We are small, yet we can think about the whole. Our lives are brief, yet our minds reach across billions of years. We stand on one planet, yet our thoughts span galaxies. This contrast does not diminish us. Instead, it enlarges us. The ability to imagine and to understand makes human life a vessel for cosmic reflection. The beauty of wonder is that it does not require mastery. You need not know the details of stellar nucleosynthesis to marvel at the glow of a star. You need not understand relativity to be moved by the curve of a galaxy. Knowledge deepens wonder, but wonder also exists without it, arising simply from the encounter with something vast. At the same time, wonder carries responsibility. To feel awe at the fragility of Earth is to sense the importance of caring for it. To marvel at the possibility of other worlds is to appreciate the one we inhabit. Wonder connects knowledge to value, showing us that science is not only about what is true but also about what is meaningful. In this way, human wonder is not separate from the cosmos, it is part of it. Our capacity to ask questions, to gaze upward, to feel awe, is itself a product of stardust shaped into consciousness. When we wonder about the universe is, in a sense, wondering about itself. The atoms forged in ancient stars have become the eyes that look back at those stars, the minds that think about their histories. This realization does not make us central, but it does make us connected. We are neither the rulers of the cosmos nor its bystanders. We are participants in it, threads of awareness within its unfolding. Our wonder is not a distraction from the science, it is one of its outcomes, one of the gifts of knowledge. As the chapters of this story draw toward their close, it is worth pausing here. Human wonder is not an afterthought, it is the bridge between understanding and meaning. The galaxies and stars will endure whether or not we watch them. But for us, the act of watching, of listening, of marveling, turns cold numbers into luminous experience. So when you look upward, remember that you are not only seeing the universe, you are part of the dialogue with it. Your wonder is as real as the light of the stars, part of the fabric of existence, fleeting yet profound, small yet vast in its reach. We have traveled together across scales and stories, from the birth of stars to the fate of galaxies, from the smallest particles to the largest structures. Along the way, we have touched the mysteries of dark matter and dark energy, the patience of light, the cycles of creation and renewal. Each chapter has been a step through the infinity of space, not to master it, but to rest within its vastness. As the story draws to its close, it is worth remembering that infinity does not ask for completion. We are not meant to see every detail or answer every question. Instead, we are invited to marvel at what is revealed, and to find peace in what remains unknown. Mystery is not absence but depth, a reminder that reality is larger than our grasp, yet still open to our curiosity. The universe, for all its immensity, has touched us here. In this quiet moment, every star we studied, every galaxy we imagined, is connected to us by the same matter, the same laws, the same story that began long ago. We are not outside observers but part of the unfolding, participants in the great rhythm of change and continuity. There is a calm in recognizing this connection. You do not need to hold the cosmos in your hands. It holds you already, through gravity that anchors your body to Earth, through atoms forged in ancient stars, through light that travels across ages to reach your eyes. You are within the story as much as the story is within you. The journey outward has always been, in some way, a journey inward. To look at galaxies is to confront perspective, to measure the brief span of human life against billions of years, and to find meaning not in size but in experience. Wonder is the bridge that makes this possible. It turns numbers into beauty, distances into poetry, and science into something gentle enough to fall asleep with. So as we pause now at the close, let yourself rest. The questions will remain, but they do not demand answers tonight. The stars will continue their courses, galaxies will continue their dance, cycles will turn as they always have. You can set them down for now, knowing they will still be there when you wish to pick them up again. Perhaps your eyes are heavy, perhaps your thoughts are slower. That is the gift of this quiet and unfolding that carries you not only through knowledge but into stillness. And if sleep has not yet come, it does not matter. The journey itself is rest, each chapter a step into calm reflection, each word a gentle companion for the night. From the first welcome to this final farewell, we have walked together through infinity, guided not by urgency but by patience, not by answers but by wonder. And now, at the edge of this story, we step into silence. We from Sleeping with Science wish you a good night.